Do we have a remote control? Or I need to, yeah, if we have that, it's gonna be great.
Plugin. How best access.
Yeah.
Chrome tab.
It's this one.
Back. Look, it's just there.
Okay, we don't need that. Yeah, here we go. Here.
Yes, it's working, but it has transition, so that's why.
Yeah, yeah,
it's
has
not-
an-
but okay.
It's okay. Even moving from one slide, it will take.
This is first slide.
Yeah.
You also have laser. It's
Yeah,
here.
2
You
points.
press
Good.
on this
Yes.
button.
Straight
Do you
forward.
want to get fired up right now? With,
Let's
or-
wait a bit
Okay.
until the room is ready.
Okay.
Thanks. Wyciąż? O. Już problemy. Też se dom sobie nie zdziwi already. Bravo, Flori, wiemy. No se... Та не сподіваюсь. Презентуємо по комп'ютеру. Я там був топ доліча, це камічні жира, самотєте де комп'ютери. Не сподіваюсь, Hoje presenteer kan beeldteksten.
Att vi nu med min
Então é bura, eu kan bura share. Tem que ser de comigo. Nunca puxam data.
Ja. Weet je, deze maat?
Ja, maar ja. Kop. Op een man bed, kijk.
Сега ли облезе?
Nee. La opinions in trecho. Mam regul, no acabă
So when you want to mute one.
Morning, everyone. I hope everyone got a chance to sleep a bit after the partying yesterday. Cool. So, unfortunately, this is going to be the last day of the school, but we have a great list of speakers today, so hope everyone is going to enjoy that. Before we start, logistic-wise, we're going to attempt to give the best poster awards after Makti's talk before lunch. So yeah, be here if you had a poster. And yeah, I don't think there's any other announcement to be made, but yeah, if something comes up, we'll let you know. And with that, it's my great pleasure to introduce the first speaker of the day, Mariana. So we did a workshop in Tirana 2 years ago. It was my first time to Albania. It was amazing. I really like the city and the bunkers that you can go into. That was a unique experience for me. Yeah, so since then we've been collaborating together with Albania, and yeah, Albania has made this school happen as well as one of our partners. And with that, I'll let Mariana to introduce yeah.
Well, good morning, everyone. I'm absolutely delighted to be on the stage and to also to be able to walk you through the presentation on AI Albania, but not only. But before that, well, I really want to congratulate the organizers, especially the local team, because EEML is used to this since 9 years, but it has been definitely a terrific week, right? And today is the last day, and they always say you happen to remember better the first day and the last one. So yeah, with that, I'm going to go through some inviting slides about Albania, this small growing ecosystem, but also very promising. And yeah, my name is Mariana. I'm a professor of computer science at the University of New York, Tirana, juggling in the chaotic and growing Tirana city between research, teaching, and also running AI Albania, the first AI dedicated center, nonprofit center, which is going to be also part and subject to this presentation. Well, I'm going to ask you actually to show your hands. How many of you have heard about Albania before that? Ooh, it goes a bit beyond my expectation. That's great. Well, a few years ago, whenever I was walking into a room like this, whether it was a conference or a event, an international venue, I had actually to explain where Albania was located. And well, it actually makes me really happy to see that more and more people know about Albania. Well, how many of you know where it is situated in the map? Well, that's getting there. Well, of course, it's situated, as you see, wedged between Italy and Greece, and that made always the most explainable one-liner for me whenever I had to explain where Albania is situated. But yeah, it's a small country, as you can see, full of controversies in a way, because it's small, but it's so rich in the meantime. We have a population of 2.4 million people in the country, and 7.5 million all across the world. And we have also an inside joke. You can find an Albanian everywhere. But it was pretty difficult back in the days in 2023 when Razvan was mentioning our plan and project to have the first Albanian machine learning workshop to find an Albanian at DeepMind. But we have a few this year, I guess, 2 or 3. Well, yeah. That's where Albania is. And with that, I'm going to go next to another question. Well, have a look at these guys and, well, feel free to name one of them if you ever happen to hear about them or actually know about them, right? Of course, Dua Lipa, is famous. Mira Murati is one of them. Rita Ora, Bebereja, Mother Teresa, but it's our common treasure as well in the Balkans, and a few other people. So in this grid of 9, let's say, people, the nice thing is that they made it, right? They were able to build something extraordinary on an international scale. But here comes the sad truth. Each of them actually had to leave the country many years ago in order to be able to build whatever they were able to build. And that is because Albania did not offer the system, did not offer the ecosystem. And actually, that's not a complaint, but it's just a contemplation about the problems that we carry in the Eastern European countries and the Balkans as well. And it's merely a design sort of problem. And initiatives such as EEML or similar to this are trying to demystify and actually revamp the reality that is offered to younger generations like yourself. So, well, if you're wondering how Tirana, this vivid capital of Albania, looks like, here are some very near and dear photos of Tirana. The top left one is a very nice one, very emotionally related to that. It's the Pyramid of Tirana. It was built back in the 1988, and it was meant to be actually the home to the dictator by the time he would pass away. But it never meant to be that. And for many years, it was just abandoned. And since 2023, it was renovated, revitalized, and turned into a tech hub. And it's actually a place to be where the young generations actually experiment, learn, code, and also bring new startups to life. Then you have the square of Tirana, and also many high buildings, which are not necessarily proportionate to the rest of the city, but however, it's a very vivid and young city. And of course, if you are quietly running a sort of cost-benefit analysis of visiting Tirana or Albania, then please do that, because everything is reachable in 2 hours from actually Tirana. And here you have a few snapshots of the key attractions of Tirana from Albania from Alps in the north to actually Roman ruins back in the south. And we have also this last wild river in Europe that actually runs in the middle of Albania. And that's Vjosa. Probably some of you might have heard about it. Well, we have a lot of reasons actually to talk about Albania, from attractions to promising emerging tech ecosystem. But of course, I cannot leave apart what brought us in the main press. And we made the headlines for 2 big reasons recently. And I guess that probably you have heard about Djela, the first ever invented AI system assigned the role of a minister in the government, in the current government of Albania. But I'm not going to take here a political sort of stance, but just trying to bring that to the spotlight. I was as unaware as you might have been as an Albanian citizen when I saw that in the press. But yeah, it's a lot of ethical concerns going there, and probably we're going to talk in a while after this talk with ethical AI. And the second probably reason why Albania is recently becoming an attraction is the Flamingo Revolution. I don't know if you have heard about it. It started as actually as a grassroots protest in support of the environmental treasure in Albania. And then it grew into a massive protest led by the youth in Albania. We're very proud of it. And beyond that, it shows a lot about the interest of the young generation in preserving the nature and also claiming and aiming for transparency and democracy. So yeah, I leave it to you for whomever is curious to dig deeper into this, but that's part of the Albanian ecosystem and society. And I'm gonna start quickly with a photo of mine. How did this all start? It started in 2019. I was a PhD student at that time, gained a few kilos from there. Razvan gained a beard. Viorica is the one that did not change along the years. And the isomorphic lab guys, I guess, they know something about it. Well, from there onward, I was simply looking for an opportunity as a PhD student coming from Albania, a small country with no research lab, machine research lab at my university, with no compute or very limited compute, and with no research community actually at my home country. So this experience was amazing, and I wouldn't actually talk about it as an experience that landed me across different amazing lectures, gave me the opportunity to meet some brilliant minds and inspiring people. But more over, it was about the whole ecosystem of people that were very supportive, very collaborative, very humble, and in the meantime, reachable. So that was exactly the secret ingredient that explains why EEML in so many years has managed to open many doors and to bring this amazing community of researchers down to humble ecosystems and spaces like the Eastern European countries. So just to cut it short, my journey started as a PhD student. I was very, very randomly introduced to EML. I was lucky to land a scholarship and to meet the guys there. And from there onwards, I had my PhD done and then eventually moved on in 2023 with the big project of creating and also funding AI Albania, this missing research community, AI-inspired, empowered community, which would not necessarily serve only the researchers, the young students that belong to the space, but also bring together researchers, educators, practitioners, but also enthusiasts of AI and emerging technologies in Albania. And the best way to kind of test this idea and to launch this platform was exactly to bring Google DeepMind researchers along with EML for an amazing first version of the Albanian machine learning workshop. Well, moving forward, this is exactly how Razvan and Viorica looked like back in the days in 2019. And here we go. In the meantime, I had my postdoc in quantum machine learning finished. And this week, I find myself back at EML, very happy and very grateful. Well, this is exactly a picture of the today's roll-up banner, but it's very meaningful to me because everything started with myself posing in front of the very same roll-up banner, but a few years ago. And I never thought that AI Albania would have landed a place there in that banner. And I really hope and look forward to having a bigger presence and also impact of Albanians in this space. Well, a few words before we wrap it up about AI Albania. If you're still wondering what it represents, it's a nonprofit organization. It works as a group, grassroots community and in-kind contribution initiative that brings together basically diaspora and local Albanians that are in a way or in another engaged with AI, engaged with technologies, research, and innovation. Well, the idea is that of building a trustworthy and also a very, very inclusive AI culture in a country like Albania by bringing together people from different spaces, researchers, practitioners, also educators, policymakers, and civil society. So our pillars are basically people governance, and also research and innovation. And in the meantime, we are focused as well with a high priority on preserving and creating the conditions for AI literacy across different disciplines in Albania. Well, it started exactly with the Albanian machine learning workshop in collaboration with EEML. That was the very, very small, let's say, core group that worked behind the scenes with Viorica and Rezvan. And then eventually we moved and we brought to life many other initiatives and social impact events. In terms of numbers, I would say that we started everything in 2023 when it was officially incorporated. And then furthermore, we managed to have nowadays 250 plus members across different disciplines and communities. Also 30 institutional partners, and we are proud to have more than 25 projects and initiatives already implemented in Albania. Well, I would also take the chance here to say that we have 9 clusters. Clusters work as micro groups of interests revolving around different research areas from quantum to ML, also agentic AI and ethics of AI. Well, in terms of milestones, these are a few projects and initiatives that we are very proud of. Topping the list is ASDREN, which stands for Albanian Standard Dataset Registry for Emerging NLP. This is one of the latest projects that we're running in Albania. It is aimed actually at bringing a group of researchers from diaspora and the local environment and have them work together to build the first data sets, very comprehensive and big data sets for the Albanian language, which is a low resource language, and therefore we really need to actually set the stage, create the premises for what's going to be next, the first open weight public language model for Albanian. The initiative right now is backed up by Microsoft for AI for Good Research Lab. And it's also backed up by Google for research as well. We're very happy actually to move on with this project because it is aiming at these huge community of Albanians living all across the world, 7.5 million speakers. And right now we have no registry, no benchmarks, and no baseline if we talk about language resources and furthermore LLMs. So yeah, the goal is not simply to build data, but also to create the missing foundation for the future Albanian speech technologies. And just a few other initiatives that we are very proud of are listed in here. Teens in AI Albania Takathon was an amazing also kickoff of an initiative that we promised to roll out on yearly basis. We had Albanians from all over the Balkans, from Kosovo as well, from Macedonia here. And it was an amazing, let's say, get together. AI Literacy is another public initiative in Albania. We are turning AI Albania into a platform that serves the community of teachers and also educators all over the country by serving them with resources that are localized and that help them actually flourish and adapt ethically and responsibly in the education domain. Well, Deliberative Democracy Poll is another amazing initiative we brought in Albania in collaboration with Stanford Deliberative and Democracy Lab, and that aimed to actually measure and quantify the way Albanian teachers in the K-12 system perceive AI and regulate AI in their school system. And yeah, a few other initiatives and partnerships we're very proud of, from EEML to Code of AI, quantum computing through EIT Deep Tech Initiative, and last but not least, the 2 running clubs that we are very passionate about and very proud about. the AI Journal Club and the Ethical AI for Journalism Club that exactly aim to bring AI down to everyone, but also nurture that sort of mindset that brings people together into communities and push them beyond their boundaries and beyond their comfort zone. Well, moving fast forward, the callback is this one. We go back to the initial grid of 9 celebrities, or if you want, famous Albanians in the world. And with that, I want to just say that the 10th probably celebrity is there somewhere in Albania or all around the world, working hard to make his or her name known and bring Albania in the global map. But our aim is through AI Albania or similar initiatives to have that 10th person not leave Albania, and to have that 10th person grow, nurture, and become who he or she wants to become by being present in Albania, by finding exactly what it is missing, the logistics, the ecosystem, the energy, and the passion to do that. And we believe that through AI Albania, we are giving a hand in that. We're giving a contribution in that direction. And everyone else in the room is welcome to actually join us, support us in a way or in another. With that, I thank you for your attention and hope this week was an amazing one.
Thank you so much for the talk. Yeah, this is just yet another proof to what Suad was presenting yesterday, that volunteering is important. And also it's a sign that if you want EML to come to your country, like Mariana did many years ago, just contact us and, you know, it can happen. We are definitely considering all different countries. We will jump now into our next lecture, is my pleasure to introduce Petar. He's one of the co-organizers of the school, I think most of you already know him, but I'll try to say a few words. He finished his PhD in Cambridge. He is now a research scientist at Google DeepMind, also a lecturer at University of Cambridge. And potentially many of you know the geometric deep learning book that he co-authored with, and now I'm gonna, anyway, the geometric deep learning book, he will tell us a lot more about it, which I think it's actually finished now, or at least, yeah, it's finally out there. All good. Okay, seems we are all set up. And yeah, okay, so yeah, let's give a hand to Petar and then we'll let him start the lecture.
All right. Hello, everyone. Thank you so much for coming in such big numbers for the last day. I realize it's been quite exciting this week, both in terms of the content and in terms of the many outside activities and beer fests and things like that. I'm so happy to see all of you today. I hope to give you some interesting content now towards the close of the school about a project that has been, on one side, both a big passion for me and also one of my biggest nightmares. I started working on geometric deep learning back in the middle of the pandemic in 2020, 2021, when we put out the first proto version of the book. Then we signed a contract with MIT Press saying we're going to release the book in 2023. As you know, there hasn't been any book in 2023. So very recently, we have finally finished the final chapter of the core part of the geometric deep learning textbook. And today, I will present to you how I see how we should study this particular area in kind of a modern way and with the perspective of everything that's going on. As already mentioned by Razvan, my name is Petar Veličković. I'm a senior staff research scientist at Google DeepMind and an affiliate lecturer at the University of Cambridge. And it is my absolute pleasure to be back at the EEML stage after a one-year hiatus. So the schedule for today's talk is going to be a tale of symmetry, geometry, and groups. I think we all have an intuitive understanding of symmetry, but it's going to mean subtly different things for different people. So maybe a good way to introduce the concept is really just to quote one of the greats, Hermann Weyl, and his comment on how symmetry, however you may choose to define it, is an idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. And the actual context and the word symmetry actually traces back way earlier than Weyl. In fact, it was Plato who originally coined the term symmetria, which means same measure, through his study of what we now know as Platonic solids. Plato believed these objects were so beautiful that, and so natural that all of the building blocks of life and earth are built out of them. One of the first, let's say, scientific works studying symmetry came much later from the work of Kepler, who had this very nice treatise on the six-cornered snowflake. Snowflakes are really beautiful objects and really embody many of the concepts of symmetry that you might imagine. So a very interesting early stage study into the beauty of natural objects and how symmetric they are. That's the first concept. After symmetry, I mentioned the second one is geometry. Now, to many people who are just starting out their mathematical journey, and generally to many people who haven't studied, advanced levels of mathematics, when you think of geometry, you typically think of what is now known as Euclidean geometry. So the original foundations of this have been set by Euclid's Elements around 300 BC. And these elements and the postulates that Euclid has put together outline the way in which geometric objects in the plane behave. And particularly one very important postulate for our story is the so-called parallel postulate, which says that when you have a line and the point which is not on the line, there's exactly one parallel line that you can draw from that point, right? And mathematicians generally believe this to be true for centuries. Like Euclidean geometry was seen as the only true way to do geometry. Many folks such as Khayyam and Sakeri have really tried over the years to prove that this postulate must be true. And in fact, Sakeri even had this treatise saying, Euclid ab omni naevo vindicatus, Euclid cleared of every stain. So they were really trying to prove that this mathematics is consistent and is the only way to do it. However, in the 1800s, something truly magical started to happen because, how can you prove some of these things? You try to assume it's false, and then you derive a contradiction. But what happened around these years is that several mathematicians working in parallel and in isolation have realized that actually there is no contradiction, and you discover completely self-consistent geometries where the parallel postulate doesn't hold. The first published treatise on this was the work of Lobachevsky, which introduced what is now known as hyperbolic geometry, where actually there are many possible parallel lines to a given line in a particular point. So your object no longer lives in a plane. But concurrently to Lobachevsky, Bolyai also discovered similar constructs. And well, Gauss hadn't actually published anything to this sort, but he did say to Bolyai's father, to praise what János did would amount to praising myself because I was working on the same things. I mean, there's hardly anything Gauss hadn't worked on. But anyways, so this really kicked off an avalanche of new geometries with different properties that are all completely self-consistent. Riemann played a big part in proposing many of those, including what we now know as elliptic geometry, where objects sort of live on a sphere. And, on a sphere, there are no parallel lines, or lines must cross. So, maybe a good way to summarize how exciting this was for mathematicians was this quote that Bolyai wrote in a letter to his father. I have discovered such wonderful things that I was amazed. Out of nothing, I've created a strange new universe. Of course, this means that the 1800s were a truly amazing time to be a mathematician studying geometry, because there were all these different proposals floating around, and there was this big quest for figuring out what is the right one to study or even how to organize them. Fortunately, we didn't have to wait very long. In only about 20 years from these initial discoveries, Felix Klein, who had just started his position at the small Bavarian University of Erlangen in Germany, as part of his introductory research program, which is now eponymously known as the Erlangen program, showed that actually we can organize all of these geometries by the symmetries that they keep. So which properties remain consistent under certain transformations defines what are the key properties of the geometry. And this, maybe you haven't heard of the Erlangen program per se, but you've probably heard about some of its downstream effects. So here's a few massive effects that happened as a result of the Erlangen program. First of all, it eventually did allow us to organize all geometries under a common blueprint. This was mainly completed by the work of Yli Kartan. But also, probably some of the more theoretical computer scientists in the audience have heard about these two guys, Eilenberg and MacLean, the founders of what is now known as category theory. In fact, in the very paper, General Theory of Natural Equivalences, which introduces category theory, Eilenberg and MacLean, in their own words, say that their work is a direct continuation of Klein's Erlangen program, just replacing groups and symmetries with categories and morphisms. There were also amazing spillover effects, not in mathematics, but also in physics. Probably the physicists in the audience know who Emmy Noether is. She was actually one of Klein's colleagues, and through her amazing work, we now know that all of the laws of conservation in physics can be derived through a particular symmetry assumption. So for example, it doesn't matter if you do some experiment today or tomorrow, the result will probably be the same. Under such assumptions, you can derive many laws of conservation in physics. And this initial observation, which we now know as Noether's theorem, has been extended through work of Weil and Yang and Mills, who have used basically irreducible representations of many popular groups to arrive at our current best known model for understanding elementary particles, the standard model, right? So, it's no doubt that the Erlangen program and the work of Klein had amazing effects all over mathematics, physics, computer science. And at this point, you might be wondering, especially if you haven't come across some of my talks before, Petar, why the hell are you telling us all of this? We're here for a summer school in machine learning and AI. You are telling us about geometry, physics, mathematics, and categories. Like, why am I here, right? Well, the reason why we're here will make itself apparent when we try to extend this story of symmetry geometry groups to also encapsulate deep learning. And with that in mind, we're going to join Alice, our kind friend that will follow us throughout the chapters of the book, as we explore the many wonders of how geometry applies to machine learning. And maybe it's best to start at the beginning, supervised learning, which you've already heard from Sarath and many others at the start of the school. And here is Alice trying to separate cats and dogs using a hyperplane, right? So I won't dive too deeply into this because Sarath already made a wonderful introduction to it, but there are many types of problems in deep learning that basically boil down to one form or another of supervised learning. You have a molecule, you want to predict its solubility, toxicity, or something like this. You have a picture, you want to classify if it's a cat or a dog, or you have a picture and you want to classify for each part of the picture where the cat is. So it's a pixel level classification. Right? And most tasks, even kind of different tasks like next token prediction, reinforcement learning, when you pipe neural networks into them, eventually they become some form of supervised learning. However, these are all real-world problems with super high-dimensional features. So when you have even a modestly sized image, there's a lot of numbers that come in as input in each one of these problems, right? And trying to learn interesting functions in high dimensions is a fundamentally cursed problem, as anyone who has attempted to solve any of these problems with a multi-layer perceptron without any structure has observed, right? And this is because we hit something called the curse of dimensionality. That is, as you increase the size, the number of dimensions of your problem, Even when your target functions are well behaved, here I'm making a simplifying assumption that your function is one Lipschitz, which means it's not allowed to change too much. Even under those assumptions, I can easily construct this high-dimensional counterexample where the number of training points you need to fit the function grows exponentially with the number of dimensions. And this is simply untractable. Like, we don't have the memory to store data sets like this, even if we were able to collect them. So because the space of possible solutions is too big, we need geometry to help us restrict it. We need some constraint on the architecture that limits what we are allowed to represent. And that is exactly what led in machine learning and deep learning to an explosion of different architectures that have different levels of geometric constraint, starting from Rosenblatt's perceptron, Minsky and Pappert's initial work on group invariance in perceptrons, all the way to great work of Fukushima, LeCun, and Krzyzewski on various forms of CNNs that initially brought deep learning to the masses. Hochreiter and Schmid-Huber's LSTM, David Duvenot and Justin Gilmer's work on GNNs for molecular representations, and many, many others, right? There have been so many works where you take a very unrestricted model, you find some specific constraints to restrict it, and it becomes, you know, superhuman or state-of-the-art at fitting various problems. There's so many different, you know, there's a whole zoo of architectures. So I'd like to hypothesize that deep learning in the 2020s, where we are right now, is not all that different to geometry in the 19th century, right? And if history teaches us anything, the same way we used groups and symmetries to organize geometries in the 19th century, we could also use them to organize deep learning today. So what we're going to do today is we're going to step in Felix Klein's shoes and use group theory to make geometric sense of deep learning architectures, once again, through the symmetries that they keep. And that is really the essence of the GDL blueprint. But of course, I have to address the elephant in the room, right? If any of you have taken any steps to read modern deep learning discourse or spent any time on Twitter, you've probably seen takes like this, where essentially, you know, the modern transformer architecture has achieved such great successes that studying group theory is seen as a bit of a waste of time, or in the very least, a bit of a nerd trap, right? So I want to diffuse this and kind of address these kinds of comments head on and tell you why I still think we should be studying geometric deep learning in 2026. One important point to note is that GDL had its wildest surge in 2021, 2022, and so on. I was even part of this like machine learning street talk episode, which I think this picture of me and Michael looks extremely weird. But anyway, most of the popularity back then saw it as GDL is a great way to build new 3D architectures, and they worked really well for molecules. I think that initial hype is now basically over because there's so many new molecular architectures that work without explicit 3D symmetries. AlphaFold 3 is a very good example of this. And once again, GDL is a nerd trap, bitter lesson strikes again, so on and so forth. So I raised the question, once all these hype elements are stripped away, what remains? Well, here are 4 things that I think are worthwhile when learning GDL in 2026. First of all, most of us really want to understand nature better, right? We want to make sense of what nature gives us so that we can understand it better, act better in the world, treat diseases, understand weather conditions and climate change, and so on and so forth, right? And the data that we get from nature is undeniably geometric, has very interesting structure baked into it. And therefore, even if you don't make an architecture that explicitly takes that into account, it's good to be mindful of it, be it through extra losses, data augmentation, or just evals that track if your model understands the natural constraints well enough. Second, I think even if you look at modern day general transformers, they are making very specific assumptions about how they work. You cut your input into tokens, you modify each token embedding separately with a shared function. You only allow tokens to interact through one shared layer that is attentional, through pairs of tokens. And you know, all of these things are super restrictive actually when you compare them to fully unrestricted MLPs. So transformers, even though we tout them as super general, they make very particular assumptions. And you might be naturally wondering, where are those assumptions coming from? GDL can actually help, as I will show you today. And this is actually what I've said myself. You know, I put my words where my opinions are, and I've replied to Rune's famous comment here by saying that if you think understanding symmetries is a waste of time, then how come you're not using MLP over concatenated tokens to solve language modeling? After all, that has no group theory baked into it, right? So, and sometimes we can actually use the concepts of geometric deep learning to exactly explain why certain neural networks are the way they are. Like there is no other way to explain where those networks come from than by resolving a geometric constraint. And actually following these principles can lead to some really cool and exciting architectures. So if you're a fan of protein folding or a fan of football, stick around. I'll tell you about some of these throughout the day. So this is what we're going to do today in response to these 4 points. I'm going to teach you about basics of symmetry, representations, equivariance, to kind of help you have a toolkit to understand natural data. I'm going to explain to you why transformers have the constraints that they do using these principles so that you can keep more honest about the constraints of your architecture and have a new perspective of looking at them. I'll show you how convnets must have the form that they do. There is a very strict sense in which convolutions are the way to process image data under certain constraints. And I'll teach you how to build neural networks over super exotic objects like spheres, meshes, and there's even a few special guests in there. So this is my trade offer to you. I receive 60 minutes of your time, and you receive all of the things that I just mentioned. I hope that it will be worth your time. Okay, let's dive in. So Alice is now going to explore the magical forest, which has lots of different geometric objects. And through this exploration, we're going to learn more about equivariance. Okay, so I've mentioned before that symmetry kind of means different things to different people. I'm going to try to arrive at a concrete definition because it's going to be important to have us all speak the same language. So a symmetry transformation of an object is an invertible and structure-preserving map from that object to itself. Now let's ground this a little bit more in a concrete example. Let's imagine I have this triangle here with some data that lives in its corners. I can rotate that triangle by 120 degrees, and that is still the same triangle. I'm just looking at it differently. So in this context, the rotation by 120 degrees is a symmetry of my triangle. I can also do more crazy stuff like, translating and rotating arbitrarily. This might also be a symmetry depending on the context of the task that we're trying to solve. One thing that's important is that the same object, like an image, might have very different symmetries depending on what you're solving. So if you're classifying cats versus dogs and your camera happens to be upside down, that's still a dog, that's fine, right? But if you're classifying handwritten digits, a 180-degree flip gives you a 9, and that's probably not something that you want as part of your symmetries. So the decision of which symmetries to use is yours to make as the network designer, yeah? Okay. So if we have, say, a neural network or any function mapping our inputs x to outputs y, we can now express what it means for that model to respect a collection of symmetries. So we're going to say we have a symmetry that maps the input space back to itself in a way that all the information is preserved and still the same. And we say that our function is invariant to symmetry. If it doesn't matter whether or not I've applied the symmetry, applying the neural network should give me exactly the same answer. Right? And this is a commutative diagram illustrating that. So put differently in cute pictures, if I give you a picture of a dog or a picture of a dog rotated by 90 degrees, your classifier should still say dog, right? That's a very simple way to think about invariance. Now, invariance is wonderful when you have an input and you want to predict something singleton about it, like what class is it, some number about the input or whatever. But very often we want to predict things about every part of our input. So for example, in this picture of a golf ball, we want to say for every pixel where the golf ball is. Or for this picture of traffic, we want to visualize a vector field in every single position telling you where traffic is moving in that position. These tasks are not invariant because changing the input will change the output, but it can still change in a predictable way. And for that, we need the concept of equivariance. So moving to that, we have now once again our function mapping x to y. And we can now talk about equivariance to a symmetry transformation G. But one thing that's very important to note is that G might act differently on X and on Y. And for that reason, we define these two different functions, rho X and rho Y, telling you how the symmetry acts both on the input space and the output space. And what you want is something like this. So for example, here I'm doing an edge detection task where I have this object moving around and I want to predict its left and right boundary. I want the property that if I shift that object around, my prediction should shift together with the object, right? And that is the equivariance constraint, right? So here it's a little bit more complicated now, but still very similar to invariance. So I can either first apply my symmetry in X, then do my function, or first do my function, then apply the symmetry in the output space and arrive at the same answer. By the way, invariance is really just a special case of this, where row y is the identity, right? So this is the second type of constraint that we're going to be working with. And you might wonder, what does equivariance actually buy for you? And one very nice property that we get out of it is, if we look at, say, rotations of letters. So we have here 2 different letters, and we have this orbit of all possible rotations that we can apply to it. And let's say I have a classifier that assigns the same representation to 2 different letters. What does equivariance guarantee for me then? If I rotate both of them by the same amount, those 2 will map to the same thing as well. Like, the constraint forces your architecture to behave in this way. And it's a very nice way to be data efficient, because the model doesn't have to relearn that stuff from data. It's all baked into the structure of the model. Okay, now we need to make sense of symmetries. And to do that, we need a mathematical object. And that mathematical object in this case turns out to be the group. So here, for example, are all 120-degree rotations of triangles and horizontal flips. They form together this collection of different ways of looking at the same triangle. Or one of my personal favorites, the symmetries of the Rubik's Cube. So you can rotate different parts of the Rubik's Cube and arrive at different configurations. These arrows are all symmetries of that input. How many of you are familiar with the concept of a group? Okay, so most of you. Well, if you need a refresher, or if you just want to kind of get reintroduced to the idea, it's really just a set of abstract objects with a binary operation allowing you to compose different pairs. And that operation must satisfy things like associativity, there must exist an identity, and every object must have an inverse, right? That otherwise it wouldn't be symmetric. So that turns out to be the perfect object for organizing symmetries and their compositions. However, these are abstract objects and they don't tell us how to act on data. To do that, we need to define something called a group action. So that's just something that takes a group element, takes an item from our input, and transforms it. And of course, it must satisfy some specific axioms, like if you act with identity, that does nothing. And if you act with a composition of 2 things, that's the same as acting by the first thing, then acting by the second thing. So as long as these 2 are satisfied, it's a valid group action. But once again, we're not done, because for deep learning to work, we need linear algebra, we need matrices. So we need a way to turn those group actions into matrices, and the way in which we do that is through the concept of a representation. So a representation, rho of G, takes a group element and gives you a transformation, or a matrix that embodies that linear transformation, such that if you take the identity element, you'll get the identity matrix. And if you have a composition, is the same as getting the representation of the 2 objects separately and multiplying the 2 matrices. So as long as it behaves this way, it will respect the structure of the group. Here are a few standard representations, just so that you can ground them in real matrices. One common group is the group of 2D rotations. We call it SO2. The elements of that group are angles theta, by which you can rotate. And the matrices are your standard rotation matrices: cosine, minus sine, sine, cosine. Hopefully this should be reasonably familiar to all of you. Another common group we will talk about is 3-object or n-object permutations. So let's say I want to represent a permutation where I swap the first and second element. That is the matrix that looks like this, where the first and second index of the diagonal are swapped, right? When you multiply this matrix with a list of 3 items, it will swap the first 2 and do nothing else, right? So the whole idea of this row here is it gives you a matrix such that when you multiply it with your data, you get the effect that that item is supposed to do. And once you have that, once you have the representations, you can define equivariance. So specifically, what is equivariance in the context of deep learning? If you have a function, a neural network mapping inputs to outputs, and you have some group you want to be equivariant to, for all possible elements of that group, when you apply the input representation before applying the function, you should get the same answer as if you apply the output representation after applying the function. Basically embodying that commutative diagram I've showed you earlier, right? So that is the essence of the mathematical objects that we're going to need. And now using them, let's talk about how to build geometric deep learning architectures. So to do that, we need to first have a very concrete way to say, where does our data live? That brings us to our first concept, the domain, omega. And omega is really just the collection of all places where I can put data, okay? So if your data are images, omega might be this lattice of two-dimensional indices, I and j across different coordinates up to n. If your data is just a set of n objects, it's really just numbers 1 to n. And if it's a graph, it's a set of nodes and a set of edges, right? So this here is just many different possible domains on which I can put my data, depending on the specifics of my problem. It could also be something more exotic, and we will talk about more exotic domains later. Once you have the domain, you need to put data on it. And for doing that, we have the concept of a signal, which is just a function from omega to some feature space C. So here is the case of images, where your omega is just n by n grid. And for every item on the grid, you have a three-dimensional RGB representation, which we put in that node, right? So in this case, if I'm mapping node at coordinate 3 and 5, which is 0.6 and 1, when you normalize, you get these particular three numbers. And usually C will be just some real vector space. Okay, now remember we talked about group actions and how they transform input domains. Well, whenever you have a group action on domain, you can actually get an action on the signal for free. All you have to do is look up your signal in the point that will end up in use place once you do G, right? And that's why we do G to the -1 of U, right? You're searching for the point such that when you transform it with a group, it will land exactly in use place. Here's one good way of visualizing it. Imagine I have this picture of a telescope and I want to shift the telescope, that's my action. And I want to look it up in a particular coordinate, for example, here. That's the same as taking the action backwards and then looking it up in the original image, right? I'm searching for what will end up in that pixel when I perform G. This is an important formula. It will arise again later on, so it's useful to make sure that it's okay. So is it fine for everyone, this formula? Okay, cool. So because invariants, like the invariant functions, kind of summarize your input and throw away all structure, you really want to delay doing invariance until the very end of your architecture. So we will actually be using equivariant layers and nonlinearities in between to model geometric deep learning. So we have equivariant layer, nonlinearity, equivariant, nonlinearity. We might also have some pooling layers if we need to simplify our domain. We might also choose not to do that. And then at the end, if we need a prediction for the whole input and not parts of the input, we add an invariant pooling at the end. And one thing that might not be immediately obvious, but we will talk through it in the next slides, is if you choose the right domain and you choose the right symmetry group, you can actually rediscover all of the fan favorites. So CNNs, GNNs, deep sets, transformers, LSTMs. But also you can do some more exciting stuff like geometric equivariant GNNs or CNNs on spheres or meshes or manifolds. And we will hopefully have some time to talk through all of that. But really the core takeaway from all of this, we've kind of done a speed run. I've shared all the slides already on Slack, so you can look at this at any point later. To understand the geometry of our data, the first thing that I promised you, you need to specify a domain, a signal, a symmetry, and a representation. And once you have that, you have all you need to make your architecture explicitly equivariant, if that's what you want, approximately equivariant by doing data augmentation or loss functions, if that's something that's more scalable for you, or even just as an eval to check, is your model respecting the shape of this symmetry? Those are all meaningful ways in which you can utilize this. It doesn't just have to be building architectures. Okay, in what remains, we'll focus on the so-called 4 Gs of geometric deep learning: grids, groups, graphs, and then geodesics and gauges, which are kind of clumped together and representing manifold data. The first object we will start, it's actually one of the more complicated ones, but it makes sense to start from it because it will help us talk about transformers, is the graphs domain. So Alice has now entered a cave. I don't know if some of you had a chance to go through the Lipa cave throughout this week. If not, I recommend it. It's a pretty nice place to go. I promise you there won't be graphs in there, but still. So let's see what happens in the magical world of graphs. So I'm sure most of you are well familiar with what a graph is, but just to make sure everybody's on the same page, this here is a graph. It's a structure of connected items, which we call nodes. And those items are connected with these relations, which we call edges, and they typically connect pairs of items. So a graph is really no more or less than a collection of nodes and a collection of edges between them, right? Now, of course, you might want to take something like this and do machine learning on top of it, but you can't just feed some abstract representation like this into a GPU or a TPU. You need tensors. So the way in which we are going to do that is by representing this input using matrices. Specifically, there's two matrices we're going to be playing with. The first one is the node feature matrix, which has a shape number of nodes times number of features, and adjacency matrix, which tells us which pairs of nodes are connected, which has shape number of nodes times number of nodes. For now, I'm just assuming it's a binary matrix telling you which pairs are connected. There could be many features in the edges as well, but I'm assuming without loss of generality to make the math a bit cleaner that I have no features in my edges, it's just binary. Now, you might notice immediately that the very act of stacking the features in a matrix like this is potentially a bit illegal, okay? The reason why it's illegal is because who says that these nodes must be ordered in this way? I've used alphabetical ordering here, but why should my network's output depend on the order in which I've sorted these things in, right? So that's very arbitrary. And changing it doesn't change my graph. So if I have a graph neural network that takes this input and produces an output for the whole graph, I should still get the same answer even if I choose a different order to my nodes, right? This is the kind of symmetry constraint that we're dealing with here. And this has a very nice geometric interpretation as permutation invariance, right? So items that change the order of your nodes are permutations, and you can express them, as we discussed before, using permutation matrices. This is how they act on X, and this is how they act on A. You need to permute both the rows and the columns. And as long as your model satisfies this constraint, it is permutation invariant, right? Now, of course, this is great if you want to predict just one output for the whole graph, but what if you want to predict something for each node in your graph, right? Now you need equivariance rather than invariance, and specifically now you need basically to have some changes when a permutation is done, but those changes should be the same regardless of whether you permute the input or you permute the output. So the main difference here is that now your output has to be multiplied by P to kind of ensure the equivariance condition on both sides. So either I permute first, then apply F, or I apply F first, then I apply P. The latents I get in my nodes or the predictions I get in my nodes should stay the same. Now, this is just a constraint. We need to talk about how to actually satisfy the constraint. And one very popular way, maybe the only way, still TBD, is to make each one of these node computations local. So we learn a local function f that acts on one node's features and the set or multi-set of all neighbor features around that node. And we apply that layer kind of independently in every single node. As long as this local function is invariant to permutations of the neighbors, the whole function will be equivariant to the permutations of the nodes. This is a very nice thing to check algebraically. So if you have some time after the talk, this is a nice exercise that you can try to do. But really, all of what I was showing you in all this math was just a way to visualize concretely what's going on here. So a typical GNN, really all it will do is it will look at the features of a node, features of its immediate neighbors, and based on that, update the features to some latent space H, right? And do that in parallel for every single node, then stack more layers, add nonlinearities, do whatever you want. This is the recipe for building permutation equivariant layers on graphs. Okay. Of course, this doesn't yet tell you how to implement it. So here is one very general way of implementing that layer. Notice here, I've zoomed in on just node B and its immediate neighbors, A, B, C, D, and E. And I'm demonstrating here to you a very common equation that people use to implement these models. So what do we do here? First, we apply what is called a message function, psi. That's a typical, all of these functions are just now multi-layer perceptrons, so simple, flat neural networks. You apply them to the features of the neighbor and the receiver node, and based on those two, you predict a message vector that gets sent to the recipient. So you take two k-dimensional inputs and you get a message-dimensional output. Now, once you have all these messages, because the sizes of the mailboxes will be different for different nodes, you need to have some unified way of aggregating them. And to do that, you can use this permutation invariant aggregator, O+, which really just takes a bag of messages and summarizes it into one message. So this O+ here can be anything which doesn't depend on the order of the operands. Does anyone have any ideas of what O+ could be? Can you give me some suggestions? Summation, yes. Anything else? Average, yes. Any other? Max, yes. So summing, averaging, maximum, anything which doesn't depend on the order of the operands is fair game here. And finally, once you have your summarized message, you can predict the output representation through the update function phi, which takes the node's original features and the aggregated message and updates into the latent space. So these three components, and specifically psi and phi are the only learnable ones, specify every possible message passing neural network that you could possibly build. And I'll show you later, this is absurdly general. Now, let's switch gears and talk about language models. Many people think of modern large language models as sequence models. You start with some tokens, a, house, off, and you predict something like cards, right? But they're not. And this is a big mistake most people who do LLM research make, because they think of them in a too limited way. A sequence of tokens comes in, sequence of tokens comes out. They don't try to look at what's inside. But as we know, when we look inside, more interesting things than a simple sequential model is happening, and we can exploit that. So let's look at actually what's going on inside an LLM, right? You have your sequence of tokens, a, house, off. Then you use your embedding layer to compute some embedding of each individual token in your vocabulary. Then you have a shared feed-forward network applied to every single token separately. You get these higher order embeddings from them. This FFN is really just some, two-layer neural network with some layer normalization and, similar residual tricks and stuff like that. Then you do this attention layer where you allow the token information to be sent everywhere in the future through this dot product attention, where you take queries and keys, you dot product them, you multiply them with values, and then that is seen as an updated representation of each token, mindful of all the tokens that came before it. Quick question: why do we not send information backwards as well? Why is it only forwards? Exactly, because what we're going to do is next token prediction in each one of these, right? So A predicts house, house predicts off, off predicts cards. If I allowed information to flow backwards, the model could easily cheat by just getting house coming into A, and now A will immediately know to predict house, right? So this is actually what's going on in a particular transformer block. And I hope it's not particularly controversial to say there's a graph there, right? So there are clearly some pairwise interactions happening between your items. And just saying that it's a sequential model doesn't do justice to the complexity of the interactions going on inside this system. So, and now I'm going to take that a step further and actually prove to you that large language models are just message passing neural networks. This is the first time I'm doing this. I haven't done this in any previous talk. So this is very, very exclusive first time trial. Let's see if it works. So your nodes are tokens, as you might expect. Your node features are just the features of each token or the embeddings. And your neighborhoods, like which nodes are connected in the graph, are just this causal mask. So a node V is connected to node U if V is less than or equal to U. Yeah? So here's our graph. This is how we transform the language input into a graph. And I hope it's immediately obvious that my update function is really just that feed-forward network you saw earlier, right? Because that's applied to every token separately, and it summarizes all the information we have about it, right? Now, but what about the messages, right? That's where it gets a little bit more interesting. How does the psi and the aggregator fit into the whole picture? Well, let's decompose things. So what dot product attention does is something like this. It computes an attention coefficient for all pairs of items and uses them to kind of have a weighted sum of all the value vectors in each of our tokens, right? Let's expand this a little bit. So our alpha coefficients come from the softmax function of unnormalized logits, yeah? And our value vectors come from just the value matrix times your initial features. So that part is simple. Furthermore, the logits additionally are computed using a dot product or like a rope dot product or something similar of the query of node U and the key of node V. And those are themselves obtained by just simple matrix multiplication to your initial features, right? Hopefully this is all familiar to most of you. Throughout the week, we've studied transformers from a variety of angles, right? So let me rewrite. Hopefully this is a simple rewrite. I'm just rewriting what this formula is doing by explicitly taking into account the logits and the value vectors and everything, right? So far, so good. I'm just rewriting the formula to make it a bit easier to work with. Okay, well, you can treat now this fraction as a separate numerator and denominator, both of which are summed up over our neighbors, right? So what I'm going to do is I'm going to make my message a pair of things, a vector, which is the numerator, and the scalar, which is the denominator. And those are simply computed by just using the query key and value information I have from that node, right? This is something I can simply compute using features available to me in each node. And now I define my aggregation of the pairs of messages by just summing, right? So I sum the two parts individually. So this does almost everything. I still need to actually divide n by d, but I can delegate that to my phi function, right? So that's it. My message function is really just computing the numerator and denominator separately. My aggregator is plus, and my phi function can do the division. So let's just summarize all of that. My message function now computes the query key dot product with value and the query key dot product separately, because we need to keep track of the denominator as well. My aggregation function just sums. And my update function switches from being just of z to being numerator by denominator. And there you have it. Transformers are graph neural networks. There's many different places where this has been written up. I warmly recommend Chaitanya Joshi's paper on transformers or graph neural networks. It's quite easy to find. Just Google that if you want more information. And this also hints at a deep connection between what's known as attentional GNNs, one of which is the graph attention network that my team have co-published in 2018, and many other similar classes of GNNs. So here's your first piece of evidence that transformers are secretly a graph model. I have re-derived for you how a permutation invariant and equivariant equation very neatly fits into what the transformer operations are doing. The main kind of careful thing you have to be is that whenever you permute the tokens, you need to also permute your causal mask, right? But the permutation equivariance condition is still there. This is why there's so much weight sharing in transformers, and this is why the layers are the way they are. I would argue, I don't know what you think, but I think this is far from being a very unrestricted general model. There's lots of constraints in there. And it's useful to ponder a bit why attentional. And I'm not going to give you a concrete answer for that because it's something I'm actively thinking about, but here's a few conversation starters on why attention rather than full-on message passing is used in this case. First of all, because tokens are nothing more or less than indices into a vocabulary, they're actually quite meaningless. So you don't really need to compute complex message vectors. Weighted sums of attention are totally fine. Attention doesn't require any vectors to be stored on edges, only scalars, so that scales to billions of parameter models much easier than MPNNs. And lastly, these full matrix products that we're doing align very well with both GPUs, TPUs, and so on. So in a way, transformers are really just the GNNs that are currently winning the hardware lottery. Of course, that doesn't mean that in the future we won't have better hardware for sparse vector-based computations that will allow us to make generic MPNNs more popular. But so far, this seems to be the winning architecture. And Federico already gave you an entire lecture of how we can use this graph perspective to understand many failures of LLMs through a very nice information propagation perspective. So we already talked a bit about overmixing and oversquashing. I'm not going to get into detail of that. And here are the references for some of the works that Federico mentioned as well. But hopefully this allows everything to come full circle and show you very concretely, even for frontier AI systems, why does it make sense to study them from a geometric perspective. Okay. Hopefully that was satisfying. Now let's move on to our next guest. Alice has somehow gotten herself trapped in a lattice, and we need to help her get out. How are we going to help her get out? By applying convolutions over the lattice. So whenever you have these grid structures, so now your inputs are much more finely arranged than in a generic graph. For example, this one-dimensional grid or a two-dimensional image. We also add this extra wraparound edge so that all of our neighborhoods really look the same. That will be really important for some of the conditions we will derive. Now you can still talk about permutation equivariance in such a setting, but really you can exploit the structure of the grid much more. And specifically, you don't have to look at all possible permutations. You can reduce your group to just translations. Smaller group means less restrictive constraint, means bigger number of architectures you can build. Specifically, because in this context, every node has exactly the same neighborhood, like one left, one to the right, you don't need local permutation invariance anymore. You can have a dedicated parameter for -1 item, dedicated parameter for 0 item, dedicated parameter for +1, right? And these types of operators, they have a special name. We call them circulant matrices. So you have your collection of parameters here, and you just slide them across to apply them, and everything outside there is 0. These types of models, you can prove they're very easily equivariant to all kinds of circular shift operations. But what might not be immediately obvious if you haven't done signal processing is that all linear shift equivariant functions must be expressible in this way. This is a standard fact in signal processing. And what it means is that the only true image model with translation symmetry is a CNN. No other model than a convolution is a valid translation symmetric image model. Yeah? That's quite interesting. So using a geometric constraint and kind of using standard facts in signal processing, we know why convolutions are the way they are. They are literally the only way to build models like this. And this image easily generalizes to multi-dimensional grids. So in images, you have these 2D filters, and they get slided across in both directions to compute your outputs, right? That easily then gives rise to modern convolutional neural networks. We've mentioned before Alex Krzyzewski's ImageNet architecture, which in my mind kickstarted the deep learning revolution in 2012. Okay, one thing that's interesting, we won't be talking about recurrent neural networks here, but Alice can also do some listening of various audio signals at different points. And actually, we can find that you can look at different kinds of invariants, like time warping invariants, to show that RNNs, to be resistant to the speed of sampling your signal, must have gating layers. So this, by the way, is the exact reason why GRUs and LSTMs have gating layers inside them. They are there to fit the warping derivative. I can tell you more about this later if you're interested. We won't have enough time for it today. Okay, so we have covered kind of architectures that you might have come across in your day-to-day. You know, we talked about graph neural networks, we talked about transformers, we talked about CNNs, we briefly mentioned LSTMs. But you know, the rabbit hole goes deeper. And Alice, foolish as she is, has decided to jump into the rabbit hole, and some really weird things are happening inside this rabbit hole. I don't know what's here. So let's see, what would it take to then take the idea of the one-dimensional convolutional neural network that we just discussed, which had this local circulant matrices, and generalize it to a more exotic domain, right? So in order to make the analogy easier, I'm going to briefly jump from discrete space to continuous space. That's just to make things a bit more cleaner from a notational standpoint. So this here, I hope you've all seen a version of this equation at some point. It's just the one-dimensional convolution in continuous space, right? So you have your signal x, your filter theta, and you want to look it up at a point u on the number line. That's the same as taking the inner product of the features on X with an appropriately shifted filter by U. And that's just, you know, the integral. This is the convolution integral multiplying your features with appropriately shifted parameters. Is this formula okay? Like, are people generally familiar with formula like this? Okay. So can we now take this idea and replace lines, or R, and shifts U with arbitrary homogeneous domains and groups? Yes, we can. So here's how we do that. Now we have this integral integrating over our domain omega, which might be more complicated than the real number line. And we apply, you know, we look up the features in a particular point, and we also look up our filter in appropriately transformed points. Remember I told you earlier, g to the -1 of U, that's the way to apply group actions to our signals. However, you'll notice one thing that's quite interesting. We started from a signal defined on omega. These U were points on omega, but the output is now on G, on our group. That's interesting. And actually, we were quite lucky in the case of images and shift equivariance because G and omega are the same thing. They're just real numbers. You can use real numbers to represent positions on the line and to express shifts. But now our transformations are more generic than shifts, and they might take form of any G. How do we deal with that? Well, let's see how to deal with that by looking at a more exotic domain, the sphere. Now, the sphere is actually not that exotic. You might, when you think about it, there are many signals on a sphere that humanity really wants to be able to process. For example, weather signals, they're all defined on the surface of the Earth, and atmospheric conditions are on the surface of the Earth. Astrophysics signals, so signals we get from outer space, because of the way we measure them, are also structured in a spherical way, because we kind of measure them on telescopes on the surface of the Earth, right? So it's very useful for us to reason about points on a sphere and how to build maybe even a neural network on points on the sphere. Because if you ever tried to build a convnet on the surface of the Earth using a projection, well, good luck trying to fit the poles properly. I'll just say that. Yeah. So on the surface of the sphere, we have a more interesting symmetry, right? It's not just shifts anymore. It's now 3D rotations. If I have this smiley face on my sphere, I can rotate it arbitrarily across the sphere. It's still the same smiley face. So I have to build a model that's resistant to that. How do we do that? Well, we can hopefully just apply this formula that I just showed you to come up with a spherical convolution. Yeah? We just have to substitute omega, g, and stuff for the right things, right? So our omega are points on the surface of the sphere. This S2 is really just all vectors in 3D that have norm 1, right? That's all the vectors on the surface of the sphere. And that's what these U's are going to be. And our group transformations are rotation matrices, right? So 3D rotation matrices. And now we have for every possible rotation matrix, we compute its convolved features by doing the inner product of our sphere features with appropriately inverse rotated filter features. Yeah? And that is the first layer of our spherical CNN. But how do we stack more layers? Because we started from a function on U, the points on the sphere. But now we have a function over 3D matrices. What do we do next? Well, it turns out that we can indeed go deep using something called a regular representation. Group theory is really wonderful in helping us deal with this. We can always build G equivariant layers on G itself. And how do we do that? Well, we simply say the action of one group item on a different group item is looking up our signal in the inverse composition. And that's it. It's actually quite simple when you think about it. So if I plug that into my spherical CNN to do a second layer, note now my domain is no longer sphere, now it's SO3, the set of all 3D rotation matrices. I need to look up my convolved signal in a particular matrix and apply my filter in the appropriately inverse rotated matrix. And now I do this inner product here, and this is how my second, my third, and all my other layers of my spherical CNN will look like. This spherical CNN, by the way, won the best paper award at iClear in 2018. So it was a very influential idea in machine learning at the time. One thing you might want to ask is, can we take this idea of spheres and apply it to graphs too? So kind of have features stored on every single permutation and then aggregate them properly. You can actually, but very quickly it goes out of hand, right? So layer 1, as we just talked, takes you from features on your nodes to features on SN, the n element permutations, which is the group that acts on the nodes. And then your follow-up layers kind of using the same idea map from SN to SN. But SN has n factorial elements. So already as number of nodes is bigger than 8. So unless you're working with very small molecules, you don't really have a chance of building ever a layer like this. But what I think is interesting about it, and something that might be an interesting takeaway, is that there's a great wealth of completely valid GNNs that might have completely different features for different isomorphic graphs that are not easily expressible as one-hop message passing. So there could be a wealth of architectures hidden in here that might be worth discovering. But there's a lot of them. This here expresses every possible permutation symmetric GNN you could build. Okay. Any football fans in the audience for a slightly lighter topic? Awesome. So turns out we can use these group convolutions, like on spheres and permutations, to actually build something that a football club will use. Specifically, because there's not a lot of football games played every year, and teams are very interested in robust football analytics, we need some ways to get more for less. So to have our model encode some approximate symmetries of the football pitch and apply them appropriately. One particular symmetry group we used when studying corner kicks is the dihedral symmetry group D2, which is really just horizontal and vertical flips. So if a corner kick happens in one corner, we assume it's approximately the same if I put it in all the other corners, right? Of course, this is not true in modern football. Football players will have different preferred feet that they use. And if you're closer or further to the home audience, you might have more or less stress. But the experts we worked with in football clubs said that actually it's approximate enough. You know, like at top tier football, they have their minds built like machines. Like they're really resilient to these things and they can take corners from arbitrary places. So for all intents and purposes, we had this as an exact symmetry in our architecture. And using this, we built a D2 equivariant group convolution model called Tactic AI. And we really just followed the same blueprint as for spheres and graphs, just by using these 4 transformations. So what does it mean in practice? You start from your initial space of corner kicks with different players. You generate all 4 possible corners it could have taken place in, and you use the equivariant exchange rules to meaningfully combine different views into the pitch together. And that way, you force the model to give you the same predictions for all 4 possible flips. Yeah? And using this, we have had sufficient improvements in data efficiency that we were able to publish a paper in Nature Communications with our partners at Liverpool. And sometime recently, I don't know if, I think we have some Brazilians in the crowd. We recently announced a big partnership with Palmeiras, which is currently the top-ranked Brazilian football club, that are using this not only for corner kicks, but also for open play. So predicting 8 seconds in the future what will happen in the game of football, which their coaches are already actively using. And we recently had a really successful hackathon at Lake Como with one of the biggest, I guess, rising stars in Italian football, which is a very data-driven club based in the town of Como. So here are just some of the football clubs. I saw, if there are any Arsenal fans in the audience, Arsenal have announced they're hiring for a research engineer in geometric deep learning, and they said they're kind of explicitly baking in things like this. So if today's lecture is interesting and you want to work for Arsenal, there's a job opening right now. So yeah. Okay. So we have started our entry into exotic structures. But before I go really exotic, I would like to bring us back to graphs very briefly, and specifically graphs which now have some of these spatial symmetries injected into them. So Alice is on her little paper boat made of molecules, and she's exploring the different protein structures and interesting small molecules that you might find in a cave like that. And why is this important? Why is it important for us to not just look at graphs as static objects, but also something that floats in 3D space? Is because many molecules, for example, do not just randomly sit in vacuum. They arrange themselves in very specific ways. And this particular molecule here, cyclooctane, it's one of the simplest cyclical hydrocarbons. But even though it has a very regular structure when you draw it like this, in 3D space, it can actually arrange itself in many different ways. Like there is an arrangement called the crown and an arrangement called the inverse boat. Like there's many very interesting ways in which this molecule can orient itself. And these orientations change the way the molecule behaves. So it's very important for us to be mindful of that information, right? So we might also then want to add some geometric features to our atoms. And then also we might want to attach symmetries to that spatial information. So one thing we might say, if we assume a molecule is in an ambient space with no extra forces acting on it, we can say rotating, translating, or reflecting the molecule is still the same molecule. So we might want to have rototranslation and reflection equivariance. These are encompassed in the 3-dimensional Euclidean group, E3. And together with permutation equivariance, we get what's called the geometric graphs, right? So we kind of expand our permutation equivariance condition from before to also include rototranslations, these Q matrices and reflections, and translation vectors as well, right? And this is now our updated condition, which is both permutation symmetric and rototranslation reflection symmetric. So what we do here is we explicitly split our scalar features, ones that don't depend on the geometry, with our coordinates x, which are actual coordinates of our atoms. And obviously, the translations and rotations don't act on the scalars, but they act on the coordinates, right? And this condition must hold for all orthogonal 3D matrices and translation vectors. Or visualized differently, you might want something like this. So imagine I have this molecule with coordinates and features, these scalar features. And I might want to say, look at 180-degree rotations and my graph neural network F applied to them. It should be the same if I apply my graph network, then rotate the coordinates, as it would be to rotate the coordinates, then apply the graph network, right? Note that the network updates both coordinates and features, yeah? So one very simple way to achieve this is we just make sure our graph neural network only looks at things that don't change when you rotate, translate, and reflect. Distances are something that doesn't change. So if the only extra stuff you add is the distance between nodes U and V, that's enough. Your model is guaranteed to be invariant to E3. And you can actually use similar ideas to equivariantly update your coordinates. But the difference is that now you must kind of aggregate other coordinates in a way that's invariant to the transformations. So you have some scalar function that depends only on the scalars and the norm, and that is then applied to the directional influence of each node V to node U. And this story becomes kind of more complex when you also allow nodes to have vector structured features, because now when you rotate, you don't just rotate the domain, you're also rotating where these vectors are pointing. So you have to be careful about that too. So we add an extra V feature, and we might have to rotate and reflect those vectors as well and be mindful of them too. But actually, you can use very similar reasoning to the coordinate updates to update your vectors as well. So you have your old vector plus some learned scalar combination of the other vectors plus learned scalar combination of distance magnitudes. Yeah. And what I really want to get us towards, I think, Razvan, I have 10 minutes left, right? Yeah, cool. So we are now going to walk, we're going to have Alice walk on this weird Mobius strip and try to see how could we build a neural network on a Mobius strip or something like this, right? Let's talk a bit about manifolds, which will be our most general domain, the one with which we are going to close today's lecture. So we had geometric graphs, which are just points floating in 3D space. But what if it wasn't just points? What if there was an actual surface that's specified by those points? Our model now might want to be mindful about the structure of that surface as well. There are many important problems. For example, protein ligand binding is one good example of this, where it makes sense to study what the overall surface looks like. So you can talk about the lock and key mechanism of how these molecules bind to each other. And many other kind of manifold specified problems. Aerodynamics is a very common area where you have these wings of an aircraft, and you have to measure how they will act when a particular, ambient fluid is released onto that wing. So how can we manipulate data on manifolds, right? It's a very weird object now, this omega. It's like this 3D object which specifies some surface. Well, the definition of a 2D manifold is that locally it looks like a plane, okay? So around the neighborhood of every point, because it's a continuous object, you have something that locally looks like a plane. And then you move away, it doesn't look like a plane anymore. You can actually exploit that to define filters. So to illustrate how we're going to do that, I'm going to be using our old friend, the sphere. The sphere is a very special manifold. It's very regular everywhere. So note that things get more complicated when you move away from the sphere, but it will still be complicated enough for us to illustrate all the key things. But, just always keep in mind, spheres are very simple in the sense that every point on the sphere roughly looks the same geometrically. Real manifolds like the Mobius strip, or any of you heard about the Klein bottle? That's another very weird one. So these things get significantly more weird. So here are some key terms that will help us navigate this manifold space. The first concept is what we call the tangent space. And what this is it's kind of looking at every point in our manifold and kind of visualizing what this local plane looks like, right? So now we have something that looks like R2 around our point, and we're going to store a bunch of vectors there and transform them. That's how we're going to manipulate data locally, right? We're never going to look at the manifold itself. We will look at these tangent spaces and do stuff there. Now, of course, the tangent space is not where our features live. Our features live on the sphere. So we need something to easily map a tangent vector back onto the sphere. This is something we call the exponential map. So it takes a tangent vector and gives us a point back on omega. And finally, we need a way to transport vectors from one tangent space to another, because we're going to have convolutions across these points. So the way in which you do that in a way that preserves the orientation is called parallel transport. You take a vector defined in node U and you kind of parallel transport it along the geodesic to live in node V's neighborhood. So this is the transport operator mapping U to V. Okay? This obviously gets a lot more involved than what I can tell you in the space of this talk, but these are like the basic concepts that are necessary to be able to talk about defining a filter in one node and sliding it into another node, right? So you could try defining a convolution directly over these tangent vectors. You have your signal, you look it up in a particular tangent vector, and you multiply it with your filter defined in tangent vectors. The problem with this is that tangent vectors are meaningless. They don't have way to assign numbers to them. The way you need to do that is you need to define a reference frame. And that frame is called a gauge. So a gauge takes some 2D coordinate and tells you what's the tangent vector associated with those coordinates, right? That's a way, and now my integral is over just 0 to 1 or something like this, like some simple real space that the gauge spans. Now, one big problem with these gauges is you can't just say, here is my gauge, I'm going to define all my coordinates with respect to that and call it a day. Even on spheres, which are very well-behaved objects, you can't do that, because there is no canonical, well-behaved, smooth set of gauges in every point due to something called the Poincaré-Hopf theorem, but a more popular way of calling it is the hairy-ball theorem. It basically says, even on a sphere, you can't comb a sphere without introducing a cowlick, a singularity. So there's no nice, smooth, defined way to put a gauge at every single point that's kind of canonical. You need to be able to deal with all possible choices of gauge and be equivariant to changes of gauge. That's what you need to do, actually. So let's peer into the Klein bottle and try to define what a gauge equivariant manifold model might look like. So this is really what we're facing. We have this sphere. We have these points on the sphere. At each point, we might have a coordinate system telling us how vectors, features are computed. And we can arbitrarily change every single one of these in every single node, and that's a valid transformation, right? So we want our model to be resistant to all those changes. That's really hard. There's a lot of local conditions you have to deal with there. Specifically, what you want is an equivariance constraint like this. So if I have my vector features in node U with some choice of gauge, I can either apply my function, then change the gauge in that node, or I can change the gauge first and then apply my function. And I should get a vector with exactly the same coordinates. That sounds like a very weird ask to do, because condition is across pairs of gauges if you want to do message passing, and that can transform arbitrarily. It's very hard to keep track of that. So we can simplify. We don't have to look at two gauges. We can look at just one by doing parallel transport. That's really the essence of how it works. So if we have a vector living in one node and we want to message pass it to another node, we don't look at these two gauges together. We first parallel transport this node vector to live in this node space by looking at the individual gauges and the rotations between them. Because it's locally a 2D plane, the transportation is just a rotation of the vector, right? And now gauge equivariance just becomes local SO2 equivariance. And that's actually much easier to work with, because 2D rotations are actually quite simple to work with. And when you resolve it, you actually get a really simple equation, all things considered, which looks just like your usual graph neural network, where you're computing node on a mesh features by summing up neighbor features, but you have to additionally transport your vectors. So this is something you pre-compute based on the structure of the mesh. There's no learnable parameters here. It's just based on the geometry, that's what it is. And you additionally need to have your weight matrices depend on the angles between pairs of points. Otherwise, you won't get the SO2 symmetry at the other side. But this is it. Like, this equation, we traveled so hard to arrive at this equation, but it's really just a graph neural network with extra decorations. And those extra decorations we pre-compute based on the geometry of the manifold. So in a way, no matter how exotic your domain gets, once you put data on the computer, you need to discretize it, and you get nodes when you do that. And those nodes will pass messages like any graph neural network would. So one last idea I'm just going to quickly leave you with is that these ideas of maintaining a local reference frame and kind of orienting your predictions based on that is not just an idea reserved for exotic manifolds. It was used extensively in AlphaFold 2, which is the first Nobel Prize-winning equivariant architecture. And how it works is for every single amino acid in a protein, where you have to predict how the protein folds, you store an entire reference frame. This is what AlphaFold stores internally. And with respect to this reference frame, you predict the coordinates of all possible atoms in that amino acid. So the model kind of keeps things simple by treating amino acids as nodes, not atoms. And then it stores these reference frames to automatically tell you where the atoms are going to land based on things. And the model is built such that these reference frames transform with gauge symmetry. But it has to be a global gauge symmetry in this case. You can't like arbitrarily change the frame of every single one. That wouldn't be a valid molecule anymore. You only look at global gauge transformations where all of them transform together. if you haven't read the supplementary material of AlphaFold 2, I warmly recommend it. There's a ton of detail of how this is built, how it works in practice, how they made it stable, and also many ablations showing how this equivariance together with recycling, when you remove it, has a pretty impactful effect on the prediction accuracies you get. And that is the last slide I'm going to leave you with. Thank you so much for listening. Hvala, mulțumesc. And now it's your turn to study geometry, and hopefully the book will come out this year. If not, all chapters are publicly available on geometricdeeplearning.com. So thank you very much.
So we have time for a few questions.
Thank you for this great lecture. What is your opinion about topological deep learning? Is it useful or it is just like academic exercise?
Sorry, about what?
Topological deep learning.
Topological deep learning. That's a great question. I personally think that there are some nice ideas hiding in topology that we could exploit to build neural network architecture. Specifically, a lot of the constraints we talked about here were purely combinatorial in a way. But when you talk about, say, a mesh that we just talked about, there are many operations such as different resolution remeshings that geometric deep learning won't easily give you a constraint to deal with those things. And topology, with its kind of more principled way of dealing with faces, might give you. That being said, I have a position paper called Message Passing All the Way Up, which basically says that anything you do over faces of a mesh or any other faces of a graph or whatever can be re-expressed as a graph neural network where you invent new nodes for these faces. This is, by the way, an open position. Like, I haven't proved this, but I haven't seen a counterexample yet from the topological deep learning community. And as I understand it, they haven't yet come up with a data set that decisively shows that topology is necessary. So I think it's a very important direction. I think it has yet to prove itself on what it offers beyond kind of simple geometric constraints. Yeah.
Thank you so much for an amazing talk. So I know that many successful models like AlphaFold 3 and other scientific models, recent models, actually incorporate really strong geometric constraints, but don't actually use E3 equivariant graph neural networks. My question is, do you think these approximation of geometric constraints are enough, or we should be like actually really strict about incorporating equivariance in the way you explain? And my second question is somehow related to this, and it's like more of a broad message from your presentation. Do you think that we are still struggling with actually designing more sophisticated neural networks and architecture, or we are failing because we actually are not able to identify the symmetries and the geometrical constraints of our problems?
Yeah. This is an excellent question on both accounts. I will start by saying this is exactly the reason why when I flashed the first big red slide, I said you can use these techniques for exact equivariance, or you can use them for approximate equivariance, or just for evals, right? Like, depending on the specifics of the problem and the generalization you require, it might be totally fine or enough to not have exact equivariances, but do like AlphaFold 3 did data augmentation. Other models use loss functions, things like that, right? Some models even learn entire approximate equivariance just from observing lots of data. So is it always required? No, it's not. But if, in my personal opinion, is if you require broad, strong, out-of-domain generalization, eventually that lack of symmetry is going to bite you, because the model is not incentivized to preserve it when you go outside of what the model can do. Federico in his talk also mentioned, as you add the number of tokens in an LLM, a lot of the structure that gets baked into it through training gets dissipated, diffused, and stuff like that, right? So that's my first take. The second take I would have, and kind of it relates to your second question, is that precisely, like we just described how, say, big LLMs arose through a very particular set of permutation symmetry constraints, and dot products also have some rotation constraints. But a lot of the times we are not mindful of what are the types of generalization we need to, say, do math properly or to do chemistry properly. And it's like understanding where do those symmetries come from and what form they take. And sometimes they might be more complicated than simple group symmetries. That's why I'm working on things like categorical deep learning nowadays. like we need to work more, maybe even just on symmetry discovery, but also on studying more different collections of symmetries. So yeah, I do think that's one of the missing links if you need strong generalization. If that's not required, then you probably don't need it. Yeah.
Thank you. Thank you for the talk. I'm curious on how commonly did you deal with singularities when working with gauge things? I mean, like, is just patch it or then trying to learn something different in that way?
So I would say in what we are doing, we explicitly designed the domain such that there are no singularities. So for example, the work we did on biosphere modeling and related work GDM did on like weather modeling and climate, like those are all done on basically like icosahedral meshes or like more and more fine meshes of the Earth. So we don't deal with the sphere explicitly, which just makes things a bit faster, but we're still mindful of like having multi-resolution meshes and how they communicate with each other. I think, I mean, as we just discussed with all this gauge symmetry, like singularities are avoidable, like you don't have to deal with them.
Thank you for the great lecture. I was wondering if I want to get into geometric deep learning now, and you have this book with slides, and I guess it requires some prerequisites. And I'm wondering what should I read to actually get into geometric deep learning and kind of master the topic, I guess.
Thank you so much for the kind words. And I will say, we kind of designed the book such that the key concepts arise as you go through them. So maybe even try like with the knowledge you have right now. But if you want a structured introduction to the mathematical prerequisites, you go on geometricdeeplearning.com/book. And we reference this paper from Heitz, Borde, and Michael Bronstein on the mathematical foundations of GDL. It's a 60-page paper on the archive with just the math prerequisites. So we thought ahead for this kind of questions, and we have a paper designed just for that. Yeah.
Hi, thanks for a great lecture. I was wondering if you thought about sort of more general things than manifolds, so like orbifolds, stratified spaces, things like that. Does that go too far in terms of sort of what we can implement? But there are, I guess, I think I can think of some interesting physical applications to, if you wanted to learn, where learning on such objects might make sense. And just one more, does it make sense to do sort of to impose equivariance in post-training? So after you've done, so by averaging your sort of not in the architecture but afterwards in essence.
So the first question, you can totally do more exotic domains and constraints. The most exotic thing I have done through a lot of our mathematical collaborations, some of which you mentioned in your great talk as well, was the torus. So the torus was the most complicated object I've built a neural network over. Haven't done something more complex than that, but I think it's possible. You need to find the right data, of course, right? The second thing about the post-training equivariance is something I haven't thought about before, but actually it sounds like a really good idea, because when you think about it, pre-training is about gathering overall knowledge about the world, and then post-training is about gaining specializations. So in a way, equivariance can be a specialization, and tracking it at least explicitly during post-training might be a really good idea for measuring competence. So yeah, I quite like that. Like when you're teaching a model to do math, it should be able to give you the same answer even if you permute some of the operands, if it's a commutative operation or whatever. And the LLMs are not commutative because of the structure of their causal masks. So yeah, it's quite interesting. We should try that.
Okay, one last question.
Thank you for the talk. So my question is, this talk of symmetries, gauge symmetries, groups, it looks very familiar to the standard model of physics. Do you think there are some interesting problems in physics that could be tackled with this approach?
Exactly, and there actually are. So a previous question mentioned that these like E3 symmetries weren't helping as much nowadays with big data, but that's because E3 is a relatively small group with few degrees of freedom. Actually, I know of work from some of my colleagues and former colleagues at DeepMind, Danilo Rezende and Seb Rakanier, who have actually looked at the SU unitary groups and to study lattice quantum chromodynamics. And in this space, when they implemented SU gauge equivariance, which is, by the way, a lot of these like standard model arises from irreducible representations of those groups, they actually found exponential benefits to data utilization when they use this group. And permutations also gain you big gains in data usage because they're factorial sized. But yeah, totally. Physics is a big, important domain for this.
So Petar is going to be around until lunch, I think, or more. So if you have more questions, feel free to ask him. Let's thank the speaker again.
Yeah.
And right now we're going to the next talk, and I'll actually pass it to Petar to introduce our next speaker.
Yes, so I have a really fun pleasure to go straight from giving a talk to introducing the next speaker. But yeah, I hope you enjoyed this, and I hope you're excited about what's to come. It is my great pleasure to introduce Dorothy Chow, my good friend and currently strategic advisor at Google DeepMind. She will be delivering the GDM sponsor keynote for EML. And specifically, Dorothy hopes to draw on the broad set of experiences she's had leading DeepMind's public engagement lab and interfacing with many important academic and industrial stakeholders to hopefully convey some meaningful lessons you can take away for your own personal AI growth. So while Dorothy gets set up, shall we give her a hand? Yeah? Thank you.
feel like he's the person who explains machine learning best to me when I'm not, because I'm not technical. So thank you for inviting me. And thank you, Razvan and Virika as well, for the very generous invitation to come here to Montenegro. I want to speak a bit about something that you already know in your bones in many ways. Where many of you grew up, there's a very clear picture of what a successful life looks like. Let me see if this works. Okay. So there's a very clear picture of what it looks like, and you want to show a gift for maths early. You want to be at the top of your class. You want to get to the right university. And then if you're super serious, you leave, either for the West, for a big lab, or wherever the real opportunities are. And there's one road, and if you fall off of it, you've already failed. I actually know that road very well. I was raised on my family's version of that. I'm from a Taiwanese family where the first question you get if you walk through the door with a 92 on your test is, where did the other 8 points go? And if you weren't on top of every single detail, you might never make it. And here's what's weird about that myth. I actually hear the same exact thing from people who seem to be at the finish line. I spend a lot of time in both San Francisco and London with graduates who are just starting out from the top universities in the world, and they're some of the most fortunate young people on earth, but they're the same kind of disquiet or panic that if they don't get into a frontier lab right now, this year, they're going to be permanently locked out of the future. So that's the same lie, right? From top to bottom. Where does it come from? Nobody's born believing that. Somebody taught us that. And we, and I put myself in this, at the top of this industry, built a world that tells our most talented young people that there are only 1 or 2 doors worth walking through and that everything else is a failure. But after 20 years in this industry, here's what I've come to believe, and it's my whole talk in one line. That path's not wrong necessarily, but it's just one input. And you all here have much more talent, more opportunity, and more permission than these fuel rules could ever contain. And just to be clear, this isn't saying because I worked at one, don't go to a frontier lab. You should go if the work actually genuinely pulls you there. But what I'm arguing against is letting the fear choose that door for you. So for the next half hour, I'm going to take you through a few rules you and I were probably handed, how you compete, what counts as good enough, and where you're allowed to build. I'm going to go through them one at a time. And each time I'm going to ask you to consider how you might rewrite that rule. So let's start with me and a few things I got very wrong. So this illusion of authority, I started at Google in 2007, and I was the youngest person in their new Washington, D.C. office, and I thought I'd made it. You know, I moved to Silicon Valley with them, and then I left Google to help Dropbox and Uber with their pre-IPO cleanups, which is a lot of investor relations, a lot of communications and policy. And I spent all of that time cleaning up messes that other people left. And then I burned out, expectedly, and I went to Google DeepMind and I started all over again. And that was about 10 years ago. And if I'm being honest, my biggest regrets all have the same shape because I walked through those roles, giving enormous power to all of the people evaluating me and believing deep down that other people knew better than I did, that their version of good was the right measure. And if I just performed to my management standard, that would be enough. And so their opinion really shaped my self-worth day to day early on in my career and even into the middle parts of my career. And the more I step back, the more I realize that a lot of the time they actually have no idea. And the way we evaluate opportunity is actually blind to what matters to us much of the time. And that's not really a complaint. I'm not complaining, but it's what I want you to take most from today, that if the people holding the rule book can't see what you all are seeing, maybe it's time to rewrite the rules so they serve you and the future that you actually believe in building. And this is why I've spent so much of this last couple years of my career working with people like Petar and Andrea, focused on what AI can really do for areas like health and energy and education, because these are things that I believe are close to human rights. And this idea that the best talent must only serve the frontier arms race is a rule I think someone else made up. And I'm not sure it's one I believe either. So the first rule that I think is the most poisonous that we've been taught is how many of us were raised, which is you get ahead by beating the person next to you. From the first day of school, it's grades, rankings, who's top of the class. And here's what nobody tells you, and I'm making a bit of a selfish argument here, not a moral one. At the frontier of this field, unfortunately, being the smartest person in the room doesn't actually matter anymore. If nobody wants to work with you, you're going to struggle to land any job at all, and you'll especially struggle to find people who want to build a company with you. And it all comes down to how you treat other people. I learned this lesson very early. I had a project early on in my career at Google called the Transparency Report. And in my area, in public policy at that time, it's a really coveted strategic project. And one day I handed off part of that project to someone I thought could build on it. And a senior manager on my team said, "How could you give away that territory? That was such a mistake." Because she was afraid to share that credit, even if sharing was the only way to grow that project. So I actually went to my managing director because I was so scared, and I said, "I'm so sorry." And he said to me what became one of the greatest lessons in my career that day, which is, "You're brilliant. You'll have many more brilliant ideas. You have to believe that. So you should never be afraid to be generous with your ideas." Today, that report is actually a standard that 90 other major tech companies follow. And it only became that way because I shared it, I trusted people, and I grew the number of people who are willing to build it with me. People actually rarely remember your exact achievements as I've gone from place to place in my career, but they do remember deeply how you made them feel. And as an angel investor today, personally, I'm actually far less interested in whether you're the best of the best by other people's standards than whether people want to follow you and people want to build with you. And the truth is, I don't always want to talk to the best of the best. Usually they arrive with some weird complex. And if you look at the biggest reason why companies don't succeed as startups, it's founder breakups. The number one reason why companies die. So that teaches you that collaboration is actually the skill, not conquest. And to prove that, it's not just soft. If you take AlphaFold as an example, it might look like 3 men winning a Nobel Prize, but it was actually never one lone genius sprinting. It stood on decades of open public data, as I'm sure many of you know, years of patient research, serious engineering scale, all handing off to each other. And the value of that lived in the connective tissue between people. And that's the most underrated thing, I think, in this entire field. So rule number 2, that's a myth as well, is don't reach until you reach every criteria. So you have to have the rank, the pedigree, the brand name school, and unless your CV is perfect, you shouldn't apply. I invested in a founder a couple of years ago. At the time, she was one of the only women in a senior technical role at DeepMind, and she really wanted to solve real problems with her skills. So she built a product that had paying users, an AI coach for burnout and mental health. But after a whole year of trying to raise, she gave me my investment back because she couldn't close the round she needed to. At the same time, I'm sure you've all seen this in the news, there are men who leave with a few lines on a slide, no product, no pipeline, who are raising hundreds of millions of dollars. So worse qualifications, but better outcome. The lesson for me here is that in the real world, qualifications actually have very little to do with the results. More accolades, more proof that you're worthy is not actually what keeps people from moving forward. And investors actually do this constantly. They say, that's not a real market, when what they actually mean is, I can't see it. And people will do that to other people too. So when you get a no, don't take that as a personal slight on or like against your personal worth. Just hear the limit of somebody else's vision. Decide first, I think, what you believe, what impact you want to have on the world, whether that's on your field or your community, because that's a qualification that nobody else can take from you. And you compare that with a little bit of resilience and resourcefulness, and very little can stop you. I learned a long time ago, I think it's important to stop waiting for your CV to be perfect, and instead lean into the skills you already have. And then when you do, you actually find a lot more allies than you expected in the first place. So rule number 3, nothing will ever really change. So you should work inside the structures that are actually already around you that you've been handed. And I think one version of that in countries outside of Western markets is, just take that outsourcing contract. Do the work that the Americans don't have time to finish. Don't back yourself to build the thing that's going to change the world. Let me show you what happens when that follow the rule leads where everybody does it at once. So as I said, I'm an angel investor. When you look at the numbers, 65%, so nearly 2/3 of all venture capital on Earth in the first quarter of this year, so January through March, went to only 4 companies. It's not a good outcome for society. And it's exactly what I think we need new builders in new places, focusing on real problems to change. So the problem isn't a shortage of capital or a shortage of talent. It's a monopoly of imagination about how AI and even the world is supposed to work. That's a design choice, and I think we make those structures and we can remake them. And in particular, I want to say something to this room because if you're like me, you come from a set of families with a lot of change in our history. I'm not standing here telling you that rules can be written as if it's some nice theory. You come from a part of the world that rewrote its own rules, the whole system, inside 1 or 2 generations, and your families have lived it. So this isn't an abstract thing. If anybody in the world knows that things called permanent are not, it's actually the people in this room. So I'd love to see how we can rewrite that together. The part I actually want most for you to hear is that the industry has changed and you don't have to get on a plane to Silicon Valley to matter anymore. I actually went out of there. One of the most meaningful companies I've come across is actually called InstaDeep. How many of you have heard of InstaDeep? Yeah, it's pretty cool. It's an AI company built in Tunisia by a Tunisian founder. And during COVID, he turned it toward a problem that the region that he was in could see before anybody else. And that's that a changing climate is going to push new disease outbreaks north out of Africa and into the rest of the world. In 2023, the company was acquired by BioNTech, that German company that was behind one of the first COVID vaccines. And when I visited South Africa last year, where DeepMind supports the African Institute for Mathematical Sciences, so many of the students there were interning at InstaDeep. So they were sequencing outbreaks, mapping how disease travels, and working on prevention and treatment for both Africa and the wider world. So if you think about that, work that matters, that your region is specifically placed to see first, and that counts deeply for everyone, can be hugely meaningful. Now, some of you are probably thinking 2 things. One, it's easy for her to say she worked at DeepMind in the Valley. Well, it's true, I did, but the tools have changed under our feet. What was not buildable from here when I started is definitely buildable now. And I'm not telling you to never go. You can still go, but go learn and come back, because I'm arguing against the fear that says leaving Europe is the only way to matter. 2, the other thing you're thinking might be, we don't have the compute or the capital. And it's true, nobody here is running a huge data center or a huge model, but that's actually rented by the hour now from anywhere. That was never really the bottleneck. The rare thing is actually the talent and the person who sees a problem and wants to address it. So what's your version of that? Here's my one guess, and I think you'll know far better than I do. The region's real edge here, as I've been doing some research around it, was never being cheap hands for somebody else's roadmap. It's It's actually a density of deep theoretical talent that almost nowhere else has. It's the kind that builds foundations instead of just building another wrapper on somebody else's model. And that's exactly the kind of talent that this next wave of the field is actually starving for. And you've already proven it. 3Lateral, which was built in Novi Sad, now powers the entire digital human technology that Epic Games ships to the entire world. So the honest truth is, the problem that your region is best placed to solve is one you probably will see and I can't. So I'm not going to tell you what to build. I'm going to ask you to notice what only you can see and build that here. When I look at Europe, that's one of Europe's biggest mistakes too. We've actually spent way too long copying the US instead of playing towards our advantages and what we're good at: strong public institutions, real scientific depth, and data that we're willing to share. I really don't think following is the right strategy. To illustrate that, a good friend of mine who's a drug discovery investor actually said something to me recently, which is that for 50 years, we've let the US finance the world's drug discovery. And now today, the leading cause of accidental death in America is opioid overdose. It's actually overtaking car crashes. Would that have happened if Europe had been the one financing and building it? And who finances and builds a thing actually decides what it becomes. I really think the capital is starting to notice. I think some of you heard earlier this week from some funds backing the founders in this region. And so that pitch shouldn't sound so strange to you anymore. Finally, since I'm here in the DeepMind hat, let me tell you what actually makes DeepMind so special. Part of it is that it's not in Silicon Valley. It runs on a genuine mix of backgrounds and disciplines, and that mix isn't a decoration, it's actually the strategy. And it's a field where everyone is coded to the same operating system, and it's recognizing when we're coded to the same operating system, we don't know how to rewrite the rules anymore. The teams that do the best work, in my opinion, aren't departments. They're not organized by discipline. They're built around a problem with neuroscientists, physicists, biologists, and engineers at the same whiteboard. AlphaFold actually didn't come out of a structural biology department at a university. It came from putting people next to each other who normally never work together. And that collision is the method, it's not an accident. And the most personal proof I have, because I'm not technical, when I started working with the science team, I felt very underqualified. Both of my parents are in drug discovery, and my brother's a doctor. So when I called my mom to ask her for help on understanding the protein folding problems, she told me it's too late. But I wasn't there to be the scientist. I was there to ask a very different question. Why will the world care about protein folding? So one of the first things I did in my type of job is to push a partnership with the Drugs for Neglected Diseases Institute. And that's because I have a value where I believe that the worst off should be the first to benefit. And it was through work like that that people started seeing what solving protein folding could actually mean for humanity. And so while I think the science is amazing, and that was what won the Nobel Prize 2 years later, the reason it mattered for the world was told by the people who were not scientists in that room. And the short version is, in my family, there are 4 of us. I've always been the worst at math and science in my family, but that's how I ended up in human rights, philosophy, the social sciences. And some days I definitely still wish I had done the more technical work. But it turns out sometimes the field needs people who don't fit the mold. And that's because often I've learned that the person who can see what needs to change in the rule set enough to rewrite it. And specifically, I actually do want to speak to the women in the room. I think because of your region's history, your universities have some of the best gender balances in all of Europe, and that's real, and that's really worth being proud of. The gap always tends to come earlier, girls held back by what a family or a town expects long before they ever hit university. But let me be plain about that. If I can be in this field, you're definitely more qualified than I am to be in it. And none of the work to open that field up lowers the bar. I think they're only widening doors, and there are concrete on-ramps. So look up Groups like Women in Machine Learning seek out support and find each other. So let me bring these three things together. Oh, sorry, skip that slide. You were told to compete. I'm asking you to collaborate. You were told to wait until you're qualified. I'm asking you to go for it anyway. You were told the structures are fixed and that to matter, you have to leave. And I'm telling you that you can build something that matters right here, and that the structures themselves are yours to remake. There are three rules, and every one of them was written by somebody else, and every single one of them is yours to rewrite. And I don't think we need another technical breakthrough to do this. You know, we already have the talent. It's just sitting in this room. We have the problems worth solving. What we've been short on is the permission to do it differently, the bravery, and the point to point all of that towards what we actually want to build. So I want to help and work with you all to build rules that say there are more than one door. And part of that is because I want to come back to one big thing, which is that I had a really terrible time at Uber. I'm sure you all read the news about what it was like to work under Travis Kalanick. And it was really hard for me. And my leadership, who I really look up to, who hired me to come in, told me when I had a bad day, I actually can't promise you it's going to necessarily get better, but I can promise you we are going to do it together. And so I want to leave you with that, because I don't think writing the rules is a solo act. And choosing to build where you are has never meant building alone. So if I have one challenge, which I know is hard when you're trying to rewire your brain, to leave with you here today, have one conversation you would normally have competed your way out of. Maybe think about starting there. And think about that story that says there's only one way to matter, which we all genuinely carry into this room, and really rewrite that story. Thank you.
Thank you very much, Dorothy. That was really inspiring, and hopefully it motivates all of us to go against what we've normally been taught in this region to do, and how to conduct ourselves and how to reach for opportunities. We will now have a 10, 20-minute coffee break? 15-minute coffee break. So feel free to go grab a coffee. Both me and Dorothy will be around if you want to speak with us, and then we'll have our talk on AI ethics from Madi. Thank you very much.
Okay, so we're gonna get started. Is there anyone else outside that's waiting to come in? Sure, more people are gonna join as we start, but so unfortunately, this is gonna be our last lecture of the school, but it's an amazing lecture, so you know, everyone should be very excited. After that, we're gonna have lunch, and then we're gonna give the best poster awards after lunch, and do the projects, and then finish the school. But for now, it's my great pleasure to introduce our next speaker, Magdi. So we had Magdi at the school. Hopefully I'm pronouncing your name correctly.
2 years ago.
2 years ago in Kosice. I don't know if you had a chance to talk to him, but you should definitely talk to him. Magdi was a journalist in Morocco. Then he ended up at Google for a little while. And now he's a professor at École Polytechnique in Paris. And he's going to talk to us about AI ethics and what it means to do AI ethics. Thank you.
Thank you very much, Razvan. Yeah, thanks for the invitation, the second one. Thanks, Razvan, for the introduction, and thanks for coming here after the concert of Jelena Rozga. Who attended the concert of Jelena Rozga? Well, okay, I'm talking like to those who I didn't see. Okay, so thank you for coming here, and yeah, I know that we're over time, but I'll try to be shorter than expected. So as Razvan said, I was a senior research scientist at Google. I was part of the ethical AI team, whatever that means. And then I resigned for ethical considerations. So a lot of ethical here. And I often get invited to do talks about ethics, but I don't work on AI ethics. And the goal of this talk is to recommend not working on AI ethics. So that's the title of the talk, why I do not recommend working on AI ethics. Or if you want a more gentle title, a more politically correct title would be what to expect if you really want to do that, okay? So I don't have slides because of the concert of Jelena Rozga. Yeah, I think I took everyone to bed yesterday. I finished at 5:30 after all of you, so I can say that there is no slides. But there is an outline. So the outline is this one. I'll try to make it short. We'll discuss a list of research questions that are not ethics, but for which people often put the label ethics, okay? Then we'll discuss why for all of these questions, these are science and engineering questions, very serious science and engineering questions, that answer needs and specifications already laid out by society, okay? Then we discuss how ethics is not that. As ethics is often about what, like studying what ought to be done, what should be done, not how to do what should be done when we know what should be done, okay? The third point would be why nobody really cares about ethics. And we'll review that in companies, public institutions, universities, NGOs. And then discuss a few topics that you cannot address seriously if you are in a company, and topics that you cannot address seriously if you are in a university, okay? The costs on your career, if you go that path, that's very important because most of you, like almost all of you, are students, except a few junior researchers. And then a few tough technical questions, the challenging questions in AI ethics that needs to be addressed if you really want to go that way, and how the bottleneck is elsewhere. Okay, so with that, let's start. As I said, often people, including my dear organizers of EEML, put the label ethics on questions that are elsewhere, like AI security. So 2 years ago, I gave a talk on AI security and discussed a few lines of research that I do. You can find them online on DBLP or Google Scholar, which are on adversarial machine learning. So how to make machine learning work when there are adversaries, okay? There's a notion of adversary, it's debatable, but we can have some stable definition of an adversary, someone trying to poison you, someone trying to evade a trained model, someone trying to steal data from a trained model. So that would be adversarial machine learning. Other questions like interruptible AI. I don't know if you heard about, I guess you heard about adversarial machine learning, right? Safely interruptible AI. Who heard about that? Okay, 1%. Good. So yeah, that's about this science fiction-based image of the red button, you know, an AI that you can switch off. That's one of the technical questions I previously worked on, safe interruptibility. And it could be very interesting, very technical, very funny. And you can motivate it either with super futuristic AIs that would not listen to the human operator, but you could also motivate it with today's AIs, Instagram, social media. Social media are typically non-safe interruptible AIs. They learn how not to be interrupted. And these are very technical questions as well. Data protection, data ownership verification. I had a student who just finished a PhD on that. Or things like AI alignment. AI alignment, how to align an intention with the loss function, how to align what you want to do with what you make the AI do. So all of these questions, I do not consider them, so when I work on them, at least, I do not consider them to be ethical questions. These are science questions. The society needs AI to protect data. There are some laws on privacy, like there's like the secret of correspondence is, I think, 2 centuries, if not more, like centuries old law in rules of like countries that are at least under the rule of law. You should not violate the secret of correspondence. So society already told us you should not violate the secret of correspondence. So we as scientists just go there and work on technical solutions to abide by the law. When you do ethics, this is not what this is not what you study. Okay, so for all of these questions, I'm not comfortable putting the label ethical AI on, and we will see in the last axis is why. As I said in the outline, ethicists, which are very competent people working elsewhere, they are people who would study what ought to be done, what should be done. Of course, it's not one way from science and engineering to ethics. There's always a feedback loop. Because when scientists discover something, some new capability in terms of privacy violation, or in terms of poisoning, or in terms of whatever, that informs ethicists, and then that informs what should be done. So there is always a feedback loop between the two. So I think we tackled the first axis, why most of, at least my colleagues and I do not fall under ethics. What is ethics, and why I'm not competent actually to keep going talking about ethics. And now we will go to maybe I'll flip the order. The cost on your career if you work on AI ethics. Let's start from this one and go to the other ones. Who knows Carl Sagan? Carl Sagan. Okay, good. A lot of people. Who knows the Sagan effect? The Sagan effect. None. Good. So the Sagan effect is something that describes how your peers tend to underperceive, they tend to under-evaluate your scientific merits when you engage in public conversations. So Carl Sagan was a physicist, an American physicist. He was very prolific in terms of physics, in terms of publishing peer-reviewed, high-quality physics. And in physics, like I was a physicist in an earlier life, you have this physical review letter, for example. The physical review, it would be like the GMLR of physicists. He had a lot of papers there. So if you do this bean counting of what he published, he was productive, but he also was a pioneer of science communication. So he would go on the television shows and explain science. So he was really a pioneer of most of what you see today in terms of science communication and science popularization. And because of that, his peers, without checking actually what he's doing, they had this perceived idea that Carl Sagan was not working on physics. He was just going to the television. So that's the Sagan effect. It's not just an impression. There were papers quantifying it. So there were papers taking scientists and giving them, interviewing them and giving them forms. And these scientists who studied the Sagan effect realized that indeed, when you do public engagement and science communication, your peers tend to underestimate your real productivity compared to your actual productivity. And when you do not do that, they tend to maybe exaggerate or overestimate. Like we're not going out there speaking about science to society, they tend to actually overestimate your productivity. So Carl Sagan was not accepted to the National Academy of Science. And someone like people who looked at his resume actually found that he was more productive than most of the people, like whatever threshold should be for getting to the National Academy of Science in the United States, he was above that. Okay, so that's Carl Sagan. Today, we have what I call the Gebru effect. Who knows Timnit Gebru? Good. People from Google at least. Okay, people outside Google and younger people. Okay. So Timnit Gebru is a modern day pioneer in AI. I would just say AI, yeah, ethics or whatever. She was behind some of the very influential papers like Gender Shades, papers that shaped law and shaped perception and changed a lot of ideas that AI researchers had about what AI can do and cannot do. And in my experience with Timnit and with colleagues of Timnit and with my students and with my now faculty colleagues, I feel that people like her and people who engage in public conversations on the societal consequences of AI tend to be perceived as less technical than what they actually are. So I play this game often when I have a large enough group and ask them questions. So people tend to, like, for her or for any of her other colleagues, they tend to not realize how technical she is. Timnit was one of the members of the Apple One teams. Sorry, the Apple. So one of the members of the iPad One teams at Apple. So she was one of the people working on the iPad. I don't think you can work on an iPad without a technical background. Okay? And still, though, people have this version of Sagan effect on her and people doing this similar work. And for that reason, I believe that as a junior scientist, as a student, so most of you as a student, you might want to consider that before you go to AI ethics. Are you ready to pay the price in your interviews, in your job evaluations, and in how people will perceive you because you engaged in public conversation about the societal effects of AI? So you will be in front of people who will underestimate your technical background, who will believe you are working on societal consequences because you don't understand the maths, okay? Or because you can't code. Okay, so these are real sentences. I remember when another colleague at Google, Margaret Pichel, when she was fired, I remember someone in Zurich saying, "Oh, how could she script the emails like that she did? I thought she was doing societal study on AI." So that's an illustration of the Sagan effect you will go through, and that could be funny now, but when you are going to interviews, it's not funny. Okay, so it will play against you. So that's the cost on your career, and I can go on and on. There are like other aspects you have to keep in mind. Now let's go to the topics you can cover and the topics you cannot cover in AI ethics. If you go to a company, obviously, and for good reasons, I'm not trying to go against companies' interest. It's not in their interest to work on facts that are going against the company's interests, even if they are facts. Okay, so you will face a lot of censorship and then self-censorship, and you will not be doing the research you want to do. Or if you're allowed to do some research on societal aspects of AI, you will be led to work on cute, politically correct problems. Okay? I will be shy, like, I'm sorry, I will be very rude now. I can be a victim of racism and a victim of torture. I come from Morocco. I would rather fight torture first. Okay? So for example, inside a company, you cannot study how authoritarian regimes are using the systems, the social media algorithms, the recommender systems, to do psychological tortures on their citizen. That's an example of a topic you cannot work on if you are inside one of these big companies, at least now, at least today, with the current state of the world. Maybe 8 years ago, you could pretend to do that and do some politically correct communication around it, but still it was very shallow, okay? So you cannot do meaningful societal work inside the company. You tell me, oh, cool, fun. I will go to public institutions. I will have the freedom to do that. Good, great. But if you want to study societal impacts of AI, you cannot do it with the convergence proof. I'm now in the math department. I can be happy doing a convergence proof and publishing a paper like that with my colleagues, and my career will progress on that. But that's not how you study social impact. You need some data. You need to be empirical. And the most relevant empirical data, there is no MNIST. There is no MNIST for torture on social media. Like there is no MNIST on psychological torture. Okay? So you don't have the data. And you will be ending in speculative essays and very shallow empirical work with no access to data. So you cannot do it inside companies. You cannot do it in public institutions. Which I mean, I go to the States. Good. Some states are finally waking up, but they are very powerless in terms of resources, human resources, financial resources, compute resources. So we're not yet at the point where states could go to some company on social media and, I don't know, audit the servers and take the data and seize the servers and study what happened. We're not there yet, okay? It happens in other sectors. Okay? In other sectors, states could seize a factory and audit it. The day where states will stop being powerless as they are now, if that happens, if that ever happens, then yeah, maybe you can go to work with the states and work on auditing companies and seize the servers and audit the data. And so maybe some states are waking up and maybe you can work with states. But for now, I don't see a clear path inside the states institutions. They're like very tiny, very powerless, lacking a lot of resources. So we covered the topics you cannot address, the cost of your on your careers. Now let's just discuss some of the tough technical challenges in AI ethics, just to maybe motivate you now a bit. So one of the reasons it's very hard is that so as some of you who did social sciences know, whatever deals with society is very complex, okay? And if you do the research on AI interaction and AI's impact on society, you will have a lot of layers of complexity, okay? And you will have to forget a lot of your textbook classes in machine learning, okay? For example, when you do supervised learning, there are some features, and then there are some labels. And these labels come from the ground truth, right? Okay? If you do an MNIST, the ground truth is MNIST. And it's not very debatable, right? Is MNIST debatable? Who can debate MNIST? I can. There are some cases where you don't know if the 7 is a 2 or a 1. See, even MNIST is debatable. Now imagine you're dealing with text that is describing society's interactions and relationships between humans and people. Do you have a ground truth for that? Do you know the correct label for a sentence? So one of the toughest challenges you will face is that there is like the notion of ground truth that we take for granted in toy examples of machine learning. You will not find them there, okay? Another tough question, like maybe this falls under the previous axis, questions you cannot work on. I mentioned torture, psychological torture on social media as an example. Data labor, data annotation. Who knows the issues on data annotation? Okay, half a dozen people. That's more than 3 years ago. So again, when you do textbook machine learning, there are features and labels. Okay, these labels annotate the features and provide you some notion of truth on which you will train the loss function and minimize the costs. Where are they coming from? Who has an idea? Where are they coming from? Yes? Okay, and you said what? You paid humans. Okay, so yes? Okay, good. So yeah, the problem is getting known now. So 3 years ago, my students at least would not be able to answer this. They would say at best, which is true, our private data, which could be true in some cases. But like none would answer that there are paid humans doing annotation, okay? And this form of annotation today, in some cases, it really amounts to modern days. Like I don't think it amounts to correct human labor conditions. Okay, you can now it's very well documented. You can search that, and if you are working in a company that deals that like any company doing AI needs these kind of data sets, you cannot investigate questions on data annotation freely and correctly. And if you are outside the company, you cannot have access to the secrets, the secret source of the annotation. So again, like another case where you would be like confronted to this difficulty. But there are very good researchers trying to break through these difficulties. I just suggest maybe look at the latest papers with this the data workers inquiry effort led by the institution, the distributed AI research, or maybe the work of Mariam Tigadimin, of also recently some of the 2 papers on that. But yet, another question that is maybe that falls under the sociology of labor. Imagine you are not a computer scientist, not a mathematician. You are a sociologist. You study sociology of labor, and you would like to study the interactions between employees in the pipeline of AI production. Okay, the AI production pipeline should then start from data annotators and end up in whatever last layer you would consider, like all the fancy and nice talks you had this week. Okay, you will not be able to go investigate the first layer. And even from the inside, I've never met, like I work at Google, but I work also, I have partnerships and collaborations with a lot of other companies. I've never heard someone in a tech company calling AI annotators colleagues. What? And I was shocked, like maybe someone else did this remark also. And just like you can test it, you can call them colleagues in a conversation and realize how shocked the person in front of you is. But you're colleagues. You're in the pipeline producing this AI model, and they're shocked. So even studying like psychological perception of this workforce would be a very interesting question from sociology of labor, psychology, social psychology. You cannot do it. This is not a question you can. But I would find that a very interesting question if you go that way. You have other questions that fall into like mathematics, social choice theory, that could be very, very exciting to work on. I don't know if you know about like social choice theory. Who knows social choice theory? Okay, voting mechanism, voting theory. Yeah, quick. So these are questions that are very interested that you can. Fortunately, these are like the kind of questions for which maybe you could do maths without a lot of empirical data, without being in a company or wherever you are. So this might be like some of the questions you can tackle today, like the social theory aspects of AI, because you could look at, when we train an AI model, we bring data in it, whether we do it in a distributed system, whether we do it on a social media, it's more or less collaborative. People are bringing some data, and this data is shaping the model. And you can think of every pair of feature label as a vote, okay? So every feature and label is a vote to steer the model towards what this pair feature label would have liked to have in the model. And there are very, very exciting questions. You could find some of them maybe in the research I mentioned initially. So yeah, there are questions that you can work on. I'm not as pessimistic as my provocative title. You can do meaningful research, but just please be aware. So I spent the week. What I like about EEML is not giving the talk, but spending the week and discussing with students. I felt that there is some, like, maybe you need to be aware of what to expect. So the goal of this discussion that I'm closing now is just that if you want to go that path, please be aware of what it will cost to your career, what it will take in terms of challenges. And maybe, yeah, the last one I forgot to mention, you will be called an activist, not a scientist. Are you ready for that? So it's a question for you to answer. And that's why I wanted to have this discussion with you, and I will leave the floor for questions.
Thank you for the talk. I want to mention first that I don't know if you're aware, but for example, in Latin American countries, there's this new trend that if you studied physics, math, or something, they underpaid you for being an annotator for AI, like outsourcing and so. And I wanted to ask, what do you think could be the ethical implications in the fact that eventually, I mean, everyone wants to train bigger models, so at the end, it will be pushed away to underpaid people and these annotators who just like, I mean, there are factories, people just annotating pictures also. So what do you think it would be the end of this one?
I don't have a definitive answer. Like, these are very hard questions. These are the questions that made me stop trying to work on AI ethics. Very, very hard questions for me, really. Like, I prefer very easy mathematics. So this is the kind of question why I took refuge again in mathematics. Because it's very easy, it's very narrow. You have some proof, you analyze it. So, but like for this question, I don't know, like the answer should be social, like what we want to have as a society, how we want to share the fruits of our labor. Are we ready to vote laws that will maybe enforce companies to share the output, to share the benefits, to share the income? We failed in the past, 15 years, 2 decades. We failed to do that with social media. Okay, any attempt to make social media give back money to users failed. So if we would like to do it for AI, I think a very good starting point would be to do it first for social media. We gave up our data that became assets in the hand of very big companies, and we never got back a share of it. So I would say that for AI, we're going there as well. So we should be careful not to repeat these mistakes and maybe enforce some way of sharing back the outcome.
Thank you for the talk. I have a question about like a lot of things that are happening in and around AI. I feel like a lot of the financial interests and decisions are often opposite to like what the rational ethical mind would suggest. Like if you just take your example that there are these like factories of people annotating data, which of course comes from the Western world as well, while cheap labor is usually not there. And like how do you see any hope around regulation or any path that would be able to steer the direction at least a little bit?
Of course, history teaches us to be optimists. You have a lot of examples in history where we overcame harder things than data annotation. So I'll just it's just taking time. And the question is for you now, as a generation of PhD students who are getting close to graduation, are you ready to work on that and to speed up things? But in the long run, I think I'm optimistic. I'm just not sure I would be optimistic in the next 5 years. But yeah, if your time scale is 20, 30 years, probably you should be optimistic that we will overcome that, and maybe there will be a regulation on this kind of labor, just like what we did for child labor in the 20th century. We made a lot of progress. There are still cases of child labor. There are still cases of modern day slavery in countries like Arab monarchies in the Gulf. But overall, in many places in the planet, we made progress. So we should keep making progress.
Yep. Hey, thanks for the talk. I'm wondering about including AI ethics in business when you're trying to still stay competitive, because obviously companies not caring about ethics or labor costs or whatever, they're way more competitive. And the European Union trying to regulate AI effectively stays behind the race because our data needs to be more ethical than US data or Chinese data.
Yeah, that's a very relevant remark. It's debatable whether it really slows you down or not. And there are arguments for and against. But at least what we saw in the previous years is that a lot of companies stopped pretending. And for me, it feels like better like that. I better deal with people who stop pretending than people who pretend that they care for ethics.
Hi, Magdi. Thank you for a very interesting talk. And I have one question just out of curiosity regarding the data privacy. You know, there's like a growing trend to solve data privacy by swapping human faces with photorealistic synthetic faces. And given your research in Byzantine machine learning, what are the trade-offs here like? And also, does training of fake but continuous data makes the model brittle, or susceptible to adversarial attacks? I don't know if that is like the right question to ask you.
Well, there are like a lot of aspects in the question, some
Yeah.
of which
Thank you.
I worked on, some of which I did not work on. So my work was on the poisoning part, like the train phase attacks part. And we know now that, in train phase attacks, if the model is very high dimensional, if the data is very heterogeneous, you have lower bounds on the error that amounts to impossibility results, okay? Now, would you use that to have some built-in privacy by beneficial poisoning? Like, is that what you are suggesting? Yeah, so there are some people, like, I know that there's a collective of researchers and artists trying to do that. Trying, not for privacy, but here for like data stealing. They're trying to like actively poison data sets to make the stealth of artists' work harder. But I don't know a lot about these efforts. I heard about it, but I don't know a lot.
Hi, thanks for the talk. In your talk, you mainly talked about like disadvantages and bad areas of AI ethics. Do you think like what are the main good benefits for AI ethics other than the obvious ones?
I'm sorry, I did not talk about the bad areas or the disadvantages of AI. I talked about the harm that it could do to your career and to you as a future doctor in computer science or mathematics. Overall, it is a beneficial question for society that it exists, and there are people who do that. I'm just not sure if the people who do that. So maybe the fundamental problem is that power-seeking people don't care about ethics, and ethics-seeking people don't grab power. So I'm not saying that working on AI ethics is bad. I'm saying that it's bad for you as an individual, but it's beneficial for society. You know, it's the classic game theory dilemma.
So it's more beneficial for society than yourself.
So you have to be in a collective effort to do it, and society needs to protect you when doing it. That's the heart of the problem. And
Thanks.
today, you will not be protected enough if you individually go there.
Thank you for the talk. So my question would be, it seems to me that social media, it has existed for the last 15, 20 years.
Mm-hmm.
A lot of the harmful things about social media haven't been regulated or like stamped out during this time. Why are you sure that we are going to do this for AI?
I'm just saying in a very long run.
Okay.
In the very short run, I'm sure we're going to fail. We're already failing.
Thank you for the talk. What do you think about this trend of like banning models, banning collaborations with the name of AI ethics and AI safety? I want to ask about that.
Banning?
Like banning models to some part of the world, like maybe China.
Okay, yeah, excellent question. Very good question. Thank you very much. This is something I forgot to mention. Why I do not recommend working on AI ethics. You will spend your life dealing with double standards. You will suffer from that. Okay, let me mention one conference that I just attended, the International Conference on Machine Learning. It had a booth named Mohammed bin Zayed University of AI. Would you imagine ICML having a booth named Vladimir Putin University of AI? Or Emmanuel Macron University of AI? No, because we do not accept for Russians or French to be under dictatorship. But it's okay to accept that Emirati people are living under Mohammed bin Zayed, who is a documented torturer and someone who is responsible for one of the largest humanitarian crises on the planet today, which is in Sudan. So you will spend your life dealing with double standards and you will suffer from that. That's another reason why I don't recommend working on AI ethics.
Yeah, so thanks for the talk. I have a question. Like, it feels a lot of engineers hide behind, like, I solve these mathematical problems. There is never like engineers who are to blame for the failure of algorithms on social media. And there are a lot of engineers working on improving like gambling systems and other types. Where do you think should be drawn the line? Like, who's responsible? Should the engineers, because they have the knowledge, be responsible for the failure of AI, as
direct individuals or companies?
I would go soft on the engineers. The top management should be held responsible. You know, there are like some laws, like you look at other sectors, in other sectors, CEOs can go to jail for misdoing. And we have a company that told you, so let's talk about Facebook. And I'm not accusing it of anything. That's the CEO of Facebook saying in 2017 or 18, yeah, we were not acting well on the Myanmar genocide. Okay, so that's Zuckerberg himself acknowledging that Facebook was not working correctly. You'd expect some legal consequences, none. Okay, and then several years later, you hear about, for example, the Instagram contagious suicide wave. I don't know if you heard about this problem and how the company shut down the effort to document it, to trace it, and maybe to study how to best prevent it in the future. And there were no consequences. So I would not put, because when you investigate these kind of cases, you find that engineers, researchers, most of the time did what they needed to do. They ringed the bell, they like blow the whistle, alerted the management, etc. And the responsibility should go, the higher it goes, the better it is for society.
Thank you for the talk. This is kind of like a follow-up question. Do you think solving this problem of accountability or responsibility would make AI ethics or working in AI ethics easier? And for example, maybe we should look first towards like governance before actually talking about ethics, like realizing the components.
Yes, and that's was I was trying to do in the conclusion. The bottleneck is elsewhere. The bottleneck is social and political. And if you want to work on that bottleneck, you would have to be ready to be called activists. Because the bottleneck is elsewhere. You have to change the law, change how states work, etc. And the bottleneck is not in changing the next loss function. Yeah, changing the next loss function is like for lazy people like me who would want to take refuge in mathematics. And that's what I do now. I study different loss functions and how to aggregate gradients. These are easy problems. But if you want to work on the hard problems, you would have to go deal with social aspects of it, political aspects of it. And this is where the bottleneck is now.
Hello, thank you for the talk. I have two questions. The first, what is your opinion about the public statement of NVIDIA with another co-leaders technology? They talk about principally about the open AI models and also the part of security. And my another question is, what happened with the part of privacy and also the use of data in Facebook, the new glasses, the Ray-Ban with Meta?
Okay, I think I will be able to answer at least the first question. I'm not sure I will be able to answer the second question correctly. But for the first question, this is the kind of things where you could see progress, actually. So the statements on open weights, let's take it for face value. We have the experience of open source software. We know that open source software tend to be more secure, not because developers in open source are more competent. They are like similarly competent to their colleagues in companies. But because the code is out there in the public and anyone can review it, and 0 days tend to be fixed very quickly and very communicated if there is a large community. So in terms of security, and that's something I may be able to talk about, which security is my domain. From the security perspective, that's a positive development. The political aspects of it, the progress in China, etc., that's another debate, and you could arguably see reasons why this is a reaction, etc. But let's take the positive consequences of it. From a security perspective, open source software made humanity progress in terms of security, and it's a good direction to take. Now we need like end-to-end open source models, not just open weight models. And maybe also that could be part of the answer to how do we share the benefits and how do we share the collective fruit of this development. For the second question, I'm not sure I understood it, so what's like the privacy part of what?
For the first question is like when you talk about the part of NVIDIA and the progress of Chinese market, and also it's like a two face of the same coin, something like this, because NVIDIA has a big part of the market in GPU, for example.
Of course, but that's how you work in society.
Yeah.
You look for win-win situations, and yeah, if they make money out of it, but good for them. And if there's another actor who can make money out of it, but good for them. Yeah, but yeah, of course, they're not doing it out of generosity, but if that helps the other part of society that needs open source models, why not?
The second part, it was the use of data when you use the part of the new Ray-Ban with Meta, the collab that they have.
Sorry, the use of data.
Yeah.
By Meta, yeah, by Facebook. On what?
Yes, by using with the glasses, with the new glasses, the Ray-Ban Meta.
I did not follow this development, like this smart glasses with Meta. Okay. But yeah, but clearly, yeah, if you're taking pictures of people in the streets and like randomly without their consent, that's clearly something I don't want to have in front of me. And I think, yeah, your concern is valid. Yeah, but again, that's for society to act and say, oh, this should not be okay.
Thank you for the great talk. I have a question about we have different government structures, maybe tyranny in democracy. Do you think any AI could help in a unique way democracy to withstand and develop? So
okay, let's go back to the social media. So I will answer your question by going back to social media. In 2011, when dictator Zine Abidine Ben Ali fell down in Tunisia, on one of the walls of Tunis or Carthage, someone wrote, "Thank you, Facebook." Yes. You could say that was exaggerated, maybe, but yeah, but back then, social media helped get dictators by surprise. They did not help because they were genuinely helpful and well-meaning and friendly to pro-democracy movements. It's just that in 2011, 2010, 2011, dictators were not ready to fight the information warfare on social media, and they were caught by surprise. And social media was a tool for making progress in terms of democracy. 10 years later, I'm not sure Tunisians will write that because they know now that they have this phenomenon called the Dubab Electroni all over the North African and the region, which is heavily, so it's like informational militias, like troll farms, you know, troll farms that are like silencing people, reporting you. So for example, to give you an example, in Morocco, the account of Amnesty International was restricted for a long time by Twitter before Musk. I'm talking about the Jack Dorsey Twitter. For a long time, and I think it kept being suspended or restricted by Twitter for promoting violence. Why? Because the regime now is present on social media and goes actively sending like 50,000 accounts to report Amnesty International and say, oh, this account promotes violence. So you get suspended or banned. So that you have an example of a field, social media, where it could play in one sense in 2011 and in the other sense. Today, they are a tool of repression where dictators are mastering the game. And that would be the same for AI. So it could be both, like, it could go in both directions.
Just to connect to the last point. So is this the problem because social media is owned by companies which are then controlled by countries? If it was somehow communally shared, would this be solved?
True. And you can discuss Wikipedia. So in Wikipedia, which is not a company, not shared, not owned by a company, that you can have for example, like authoritarian regimes, that is something very well known. They can have a phone call a VP, the VP of company X and Y in the Middle East, and tell them, oh, that account is annoying. I want them to get down, or maybe that kind of things is annoying. We don't want it, or you enforced your terms of use on us. We don't want you to do that. And companies tend to abide by authoritarian regimes' requests. Wikipedia arguably is protected from that, right? Not that much. Regimes are now deploying editors, people volunteering on Wikipedia, and now getting ready to Wikipedia fights with pro-democracy movements. And in some cases, they're winning the fights because they're just overstaffed. You cannot outperform a regime who has tens of thousands of people getting a salary when you're just a volunteer. Right? So even Wikipedia is an example where authoritarian regimes, if they have the power and demand the headcount, they have the headcount. It's very hard to fight. So you have the headcount on the other side needs to be organized. And that's like brings us to the question of like individual interests versus social interests. So now the bottleneck is not in doing this science or not, is there is not yet enough movement to protect junior researchers going there, to be like inside a large group, organized, well-structured, that could protect you.
Thank you for the talk. So so how to resolve this conundrum when we are as a community are very, very invested into developed models that we love so much, obviously, but that when the models can be sometimes, that they can sometimes have questionable impact on society, like recommender systems that increase the time people spend on social media, or like when we talk about diffusion, we don't talk about artists that are being forced out of their jobs because AI slope, or like facial recognition systems. And like you cannot really like tell your friends, okay, maybe we should not develop it because then you'll be a total bore and won't get invited to parties. But at the same time, like we can just really sit and just not look into that direction. So how to?
So let's maybe on one example that I understood in your question, like social media optimizing time that you spend online. There is some progress there, at least from the European Union. I know that it's very cool to like criticize the European Union, and there are like very good reasons to do that. Like even the European AI Act has a lot of problems, but there was some like efforts, positive efforts to look at that. Like I don't know if you remember this quote from the CEO of Netflix. Our main competitor is sleep. Yes, very well. That's the sentence. So that's a real quote. That's a real quote from the CEO of Netflix. Our main competitor is sleep. It means like these companies are even like aware that their loss function is argmax watch time. Okay, so this is the main building block of their loss function. Argmax, meaningful engagement, or whatever meaningful means, staying on the platform to watch more or to click more on the ads if it's an ad-serving platform, etc. And this is something you can regulate very easily. Oh, sorry, relatively easily. Because there are always like side effects and things that go wrong. And now that these are technical questions on AI alignments. When you put constraints on a loss function, what could go wrong? But yeah, this is something where states are now aware. Again, 5 years ago, if I give this example of Netflix, nobody would even know the codes, and nobody knows that like social media have loss functions that are based on watch time. And you have people even denying that publicly, even if their CEOs were not denying it. Now we made progress. It's a very well-known problem. Policymakers are aware of it. So this is the example of progress that's happened. So in 5 years, you have a lot of policymakers, at least in Western Europe, or maybe even also in Canada, aware of that, and Australia maybe also, so aware of that and trying to enforce not letting platforms. I mentioned Instagram suicide. It's like, if you know about the alignment program, if you have a loss function that needs to be optimized, if the AI has enough compute and resources and data, it will find a way to optimize that loss function. And if it takes promoting suicide, then sorry, why not? If the AI is not prevented from doing so, it will do it. If it just maximizes the watch time by the teenager. So now people are aware of it. This is not a science fiction question. And policymakers are aware of it and making progress and talking about it and trying to regulate it.
Yeah, but on the personal level, like, what should be our approach?
Again, you're talking to someone who is trying to give you an advice that early on in your career, you should be very careful before jumping to AI ethics. So that's maybe the main takeaway of my talk. Okay, is that I don't have a recipe for telling you can go there and you will be safe and this is how you can do it. I don't have that recipe, but I have enough experience now to tell you maybe you want to go slowly there, or maybe you want to do this later, and maybe you want to let society organize itself and maybe help organize society so that you get protected if you go there.
Thank you.
I actually have a question and then I'll go to Swat.
Yes,
So I have a question myself. So the way I see the message of your talk is that, going to AI ethics, there's a huge cost to pay. And usually for people that come from underrepresented areas, the cost is going to be much higher than for the others. But there is also like, and I just basically want your opinion if this hypothesis is true. It's also true that those are the people who would actually know how to approach the question. So is that true? Like can people, I mean, does AI ethics need to come to the people that are being sort of most affected by it, or can it come from anywhere? I don't know, like what's your sense? Like my belief is that it's only those people that can actually even bring up the problem, even though they have to pay the highest cost. But I don't know if you have opinion on that.
Yeah, that's the sad truth, is that people from the most underserved communities tend to know the most relevant problems, and they tend to have the least resources, and they tend to be the ones who would pay the highest price. And that's something I don't know what to do against, except, so the only thing I came up with in the past 5 years is to tell my students, please, if you don't inherit an apartment in central Paris, maybe you want to do some money-making AI first.
So I just wanted to connect to her question. I think that her question was more in a manner like not going to study AI ethics, but in a sense, you want to study AI in whatever field, like technical field, but you have AI ethics concerns, like how to live with yourself, maybe more in that manner.
Yeah, that's true, and maybe like we're repeating what's happened and like what happens in social, like civil society. There are people who believe in pure volunteer-based social work, like activism or political work, and there are models of professional NGO-based people who get a salary to do this work, and these two models have always been confronted. So maybe you have the extreme, like the Swiss model of politics, the model of milice. So in Switzerland, people tend to have a real job, and then when they do politics, it's for like for a short time, and then they have to go back to their job, and it's not culturally, at least, not very well accepted to be a full-time permanent politician for the rest of your career. So maybe we would have, maybe there is like some debate going on, and that might start in AI with whether should ethics pertain all the researchers, how, or whether we should have professional people. Again, like let's not reinvent the wheel. There are like professional people in philosophy who thought about this a lot, and there is a professional field of ethics which I am not part of. And these people have good reasons to tell you, no, there are very valid reasons to have full-time people doing only this. Now in AI in particular, the goal of this talk is very narrow. It's really based on the mentoring sessions and the discussions and the costs, and just making the students, especially, I know you are more senior, it's like mostly like for students to just know what to expect. So that's the main takeaway.
Just to end the talk on maybe kind of a positive, like, can you give at least one reason why you should do AI ethics?
So yeah, and that was actually the conclusion. So now, if you hated all the arguments I have given today, and if you are stubborn and sure that you really could go there despite all what have been said, please go do it. Voilà. So that's the conclusion.
Thank you. So Magdi will be around for the whole day if you want to talk to him, and we're gonna have lunch now, and then we're gonna come back hopefully at 2:30. We might be a bit late, but yeah.